You are listening to EF Core Traps, navigating common pitfalls and building robust applications. Like and subscribe to keep up to date on our latest audiobooks. EF Core Traps, navigating common pitfalls and building robust applications. Chapter 1, The Foundations of Entity Framework Core and Why Pitfalls Matter. 1.1, What is Entity Framework Core? Entity Framework Core, often affectionately shortened to EF Core, is an indispensable tool in the modern net developer's toolkit. At its heart, EF Core is an object relational mapper, or ORM. Think of it as a highly skilled translator, perched between your meticulously crafted C# application code and your robust database system. Its fundamental role is to bridge the chasm between the object-oriented world of your C# classes and the relational world of tables, rows, and columns that databases understand. Traditionally, interacting with a database meant writing raw SQL queries, executing them, and then manually mapping the results into your application's C# objects. This process, while granular, was often tedious, error-prone, and consumed a significant amount of development time, leading to what developers often call boilerplate code, repetitive, standard code that doesn't add much unique business value. EF Core revolutionizes this by allowing you to work with plain C# objects, which we call entities. For example, if you have a product class in your application, EF Core can map it directly to a products table in your database. When you want to retrieve a product, update its details, or delete it, you simply perform operations on your product's C# object. EF Core then intelligently translates these C# operations into the appropriate database language, such as SQL commands, and handles their execution. The benefits are substantial. First and foremost, it greatly simplifies data access, freeing developers from writing vast amounts of repetitive data handling code. It offers strong type safety due to its deep integration with C, meaning that many common data access errors can be caught by the compiler even before your application runs, rather than manifesting as subtle runtime bugs. Furthermore, its seamless integration with LINQ, C#'s powerful language-integrated query feature, empowers you to write complex and expressive database queries using familiar C# syntax, enhancing both readability and maintainability. This abstraction layer not only speeds up development, but also makes your data access code more robust and less prone to common human errors. 1.2, The Promise of Simplification and the Hidden Complexities. One of EF Core's most compelling features is its initial ease of use. A developer can, with just a few configuration steps and a handful of C# classes, have an application interacting with a database almost instantly. It can feel remarkably like magic. Tables appear, relationships are managed, and data flows with what seems like minimal effort. This rapid prototyping and development speed are powerful selling points. However, this very ease of entry can be subtly deceptive. While EF Core handles a tremendous amount of database interaction behind the scenes, it's performing highly complex operations to do so. The magic is just sophisticated engineering, without a foundational understanding of these underlying mechanisms. How EF Core chooses to translate your LINQ query into SQL, how it tracks changes to your objects, or how it manages database connections. It's remarkably easy to inadvertently write code that is not just inefficient, but potentially buggy, or even harmful to your application's performance and stability. Consider the analogy of driving a modern car. Today's vehicles are incredibly sophisticated, filled with advanced computer systems managing everything from engine performance to safety features. You don't need to be a mechanic to drive one. Indeed, you can get in, start the engine, and go. But if you want to drive that car efficiently, understand its performance limits, diagnose an unusual sound, or fix something when it inevitably goes wrong, you need far more than just surface-level knowledge. Similarly, EF Core can be the powerful engine for your data-driven application, propelling you forward at speed. But without a deeper grasp of its inner workings, misusing it can lead to unexpected breakdowns, costly repairs, and a frustrating journey. 1.3, Why understanding pitfalls is crucial. Falling into common EF Core traps can have significant, real-world consequences, transforming a seemingly smooth development ride into a bumpy and expensive journey. These aren't just theoretical issues. They directly impact the very quality and viability of your applications. Performance implications. This is arguably the most common and immediately noticeable impact. Inefficient queries can turn an operation that should take milliseconds into one that grinds on for seconds or even minutes. User interfaces freeze, reports fail to load, and the entire application feels sluggish. This directly translates to frustrated users, lost productivity, and, in many cases, higher server costs. What might run smoothly on a development machine with a few test records can become a crippling bottleneck in production with real-world data volumes. Data integrity risks. Incorrect handling of concepts like concurrency or transactions can lead to disastrous scenarios. Imagine lost updates where a user's changes are overwritten by another, or inconsistent data states where related records don't match up. These issues can result in corrupted information in your database, which is a nightmare for any business relying on accurate data. Maintenance headaches. Code that unknowingly abuses EF Core's capabilities can become incredibly difficult to debug, refactor, or extend. Developers find themselves spending more time battling the ORM and understanding its surprising behavior than solving genuine business problems. This technical debt accumulates, slowing down future development and increasing the total cost of ownership. Scalability limitations. An application riddled with performance pitfalls might appear to work adequately during initial testing with a handful of users. However, it will inevitably buckle under the load of hundreds or thousands of concurrent users, preventing the application, and perhaps the business it supports, from growing effectively. Bottlenecks that were minor inconveniences under light load become immovable barriers under heavy demand. Increased cost. Beyond the direct impact on user experience and development time, inefficient database interactions consume more server resources, CPU cycles, memory, and disk input-output. For applications deployed in cloud environments, this directly translates into higher monthly hosting bills. Paying for more powerful servers just to compensate for inefficient code is a waste of valuable resources. The primary goal of this book is to equip you with the knowledge and practical strategies to recognize these common pitfalls, understand their root causes, and apply effective solutions. It's about empowering you to write robust, efficient, and maintainable data access code with EF Core, making it a powerful asset in your development toolkit rather than a source of hidden problems. 1.4 Who this book is for. This book is crafted for anyone who uses Entity Framework Core in their net applications. Whether you're building a simple web API, a complex enterprise application, or a desktop client. For junior developers. If you're just learning the ropes of EF Core, this book will serve as an invaluable guide to help you avoid common mistakes right from the start, setting you on a path to writing high-quality data access code. For mid to senior developers. If you've been using EF Core but find yourself hitting performance walls, encountering mysterious bugs, or dealing with code that's hard to maintain, this book will deepen your understanding, clarify complex concepts, and provide practical optimization techniques. For architects and technical managers. Understanding the potential pitfalls and best practices of EF Core is crucial for designing scalable and reliable data-driven applications, as well as for making informed decisions about technology choices and team training. While some familiarity with C# and basic relational database concepts, such as tables, columns, and relationships, is beneficial, this book assumes no prior deep expertise in EF Core. All EF Core-specific concepts are explained clearly and accessibly, ensuring that the content is understandable for a broad audience. 1.5 How to use this book. You can approach this book in a couple of ways. If you're new to the specific challenges of EF Core or want a comprehensive overview, reading it from cover to cover will provide a progressive buildup of knowledge, with each chapter complementing the last. Alternatively, if you're battling a specific issue, perhaps a slow query, unexpected data behavior, or a migration problem, feel free to jump directly to the relevant chapter or section. Each pitfall is explained independently, though some do build upon foundational concepts introduced earlier in the book. Throughout these pages, you'll notice a deliberate focus on describing the intent of the code, the logic behind the pitfall, and the conceptual solution, rather than displaying raw code blocks. This approach is chosen for a very specific reason. It makes the content accessible and valuable for both print and audio formats of this book. For instance, instead of showing lines of C# code to illustrate a problem, I might describe it verbally. Consider a common scenario where a few lines of C# first retrieve a collection of customer orders, and then, inside a loop, separately fetch the detailed shipping information for each of those orders. This allows the emphasis to remain firmly on understanding the problem and its solution, ensuring you grasp the underlying principles without getting bogged down in syntax. Remember, while this book provides practical solutions and insights into common EF core challenges, the official EF core documentation is an expansive and invaluable resource for delving into deeper technical details and specific API behaviors. Furthermore, the vibrant EF core community, found in places like Stack Overflow, GitHub discussions, and various technical blogs, remains an excellent source for specific scenarios and the latest insights. We'll touch on staying updated with EF core's evolving landscape in the final chapter. 1.6 Core EF Core Concepts, Brief Refresher Context. Before we dive headfirst into the traps and tricks of EF Core, let's quickly refresh ourselves on a few core concepts. This isn't a comprehensive tutorial, but rather a brief reminder of the key players you'll encounter throughout this book. Understanding these components is foundational to grasping many of the pitfalls we'll discuss. The DB context. This is your primary entry point and interaction point with the database. You can think of a DB context instance as a lightweight session or a unit of work. It's the object you use to configure how your C# entities map to your database schema, to write LINQ queries to retrieve data, and to manage the process of adding new entities, modifying existing ones, or deleting them from the database. When you call methods like save changes or execute queries, you do it through your DB context. Entities. In EF Core, entities are plain C# classes that represent the tables in your database. For example, a product class in your C# application might be mapped to a products table in your SQL Server database. EF Core is designed to automatically handle most of the mapping between the properties in your C# class, like producted, name, price, and the columns in your database table. Migrations. As your application evolves, so too does your database schema. You might add a new email property to your customer entity, which then requires a new email column in your customers table. Migrations are EF Core's robust mechanism for managing these database schema changes. They allow EF Core to generate the necessary database update scripts, like alter table commands, to evolve your database schema incrementally and safely, allowing you to move between different versions of your schema without losing data. LINQ to entities. This is how you query your data. Instead of writing raw SQL, you write LINQ queries in C# using your entity classes and properties. EF Core then takes these LINQ expressions and translates them into efficient SQL queries that are executed directly by your database. This seamless translation is one of the most powerful features of EF Core, enabling type-safe and expressive data querying. The change tracker. This is a crucial, yet sometimes complex, internal mechanism within EF Core. When you retrieve entities using a DB context, EF Core doesn't just pull the data. It also starts tracking those entities. This means it takes a snapshot of the entity's original state when it was loaded and closely monitors any subsequent changes you make to its properties. When you eventually call save changes, the change tracker detects the differences between the original state and the current state, and it then generates the appropriate insert, update, or delete commands to persist those changes back to the database. Understanding how the change tracker operates is absolutely essential to avoiding many performance and data integrity pitfalls. Its power is immense, but its nuances can catch even experienced developers off guard. With these foundational concepts in mind, let's embark on our journey to uncover and master the common pitfalls that await in the world of Entity Framework Core. Chapter 2. Querying Quagmires. From N+1 to client-side chaos. At the core of virtually every data-driven application is the ability to retrieve information from a database. This fundamental operation, often performed hundreds or thousands of times a day, is where many EF core performance problems originate. Writing a simple LINQ query might feel intuitive and natural in C, but how EF core translates that query into the underlying SQL can have dramatic and often surprising performance implications. This chapter dives into some of the most common and impactful pitfalls related to data retrieval. We'll explore how seemingly innocent coding patterns can lead to inefficient database calls, excessive data transfer, and system sluggishness. Understanding these querying quagmires is crucial for building applications that are not just functional, but also fast, responsive, and scalable. 2.1 The N+1 Problem. A performance killer. One of the most notorious and frequently encountered performance antipatterns in data access frameworks is the N+1 problem. It's deceptively simple in concept, yet can wreak havoc on application performance. What it is? The N+1 problem occurs when you make one initial database query to retrieve a list of parent or primary items, and then, for each of those N items, you execute an additional, separate database query to fetch associated or related data. This results in a total of 1 plus N database queries, where N represents the number of items in your initial list. Why it's a problem? Imagine fetching a list of 100 customer orders. Then, as you process each order in your application code, you make a separate trip to the database to find out which salesperson was assigned to that specific order. This means one query for the orders and an additional 100 queries for the salespeople, totaling 101 database requests. Each database request is not free. It incurs overhead due to network latency. The time it takes for data packets to travel between your application and the database server, and also internal database processing time. When you multiply this overhead by tens, hundreds, or even thousands of individual queries, what should be a quick operation turns into a painfully slow bottleneck, consuming valuable application server time and unnecessarily burdening your database. Example scenario: consider an application that displays a screen listing all your company's blog posts, and for each post, it needs to show the name of the author. A common but problematic approach often looks like this. First, a query fetches all the blog posts from the database. Then, your application code begins to loop through each of these blog posts. Inside this loop, for each individual blog post, another line of code is executed to retrieve its specific author from the database. If your blog has 50 posts, this translates to one query to get all the posts, followed by 50 separate queries, one for each author. This pattern scales linearly with the number of items, leading to increasingly poor performance as your data grows. How to identify? Database profiling. The most definitive way to spot an N+1 problem is by using a database profiler. These tools monitor the actual SQL queries being executed against your database. You will see a telltale pattern. One large query followed by a cascade of many small, very similar, individual queries being executed in rapid succession. For our blog example, you'd observe a single query selecting all blog posts, immediately followed by dozens of select from authors where id equals x queries, each with a different author ID. Applications slow down. From a user's perspective, the application will feel sluggish. Pages or reports that display lists of items with related data will take an unusually long time to load. If you experience a sudden and significant drop in performance whenever you retrieve and display a collection of items, and you know there's related data involved, the N+1 problem should be a prime suspect. How to fix? The fundamental solution to the N+1 problem is to load all the necessary related data in fewer database trips, ideally in a single, more comprehensive query. EF Core provides several powerful mechanisms for this. Eager loading with include. This is the most common and often the simplest solution. You explicitly tell EF Core to load related entities, such as an author with a blog post, or order items with an order, along with the primary entities in a single database round trip. For our blog post and author scenario, you would write a query that tells EF Core to retrieve the blog posts and to also include their associated author. EF Core then intelligently generates a single SQL query, typically using a join operation to retrieve all the necessary data in one go. You can also chain include calls to load deeply nested relationships, for example, loading an order, including its order items, which in turn includes details about the product for each item. Projection with select. Sometimes, you don't actually need the entire related entity object. Perhaps you only need a few properties from it, or you want to combine data from multiple related entities into a simplified structure for display, often referred to as a data transfer object, or DTO. In these situations, using the select linq operator to project your data into a new anonymous type or a specific DTO can be even more efficient. This approach tells EF-Core to generate a SQL query that retrieves only the specific columns you've selected from the various join tables, rather than all columns from all loaded entities. This minimizes network traffic and memory usage within your application. As split query. For scenarios involving very complex object graphs with multiple include statements, especially those involving collections of collections, the single SQL query generated by include can become extremely large and potentially inefficient for the database to process. These large queries can sometimes lead to a Cartesian product issue, where joins multiply rows unnecessarily before filtering, consuming excessive database memory. In such cases, EF-Core offers as split query. This instruction tells EF-Core to break down your complex query into multiple, separate SQL queries, each loading specific parts of the object graph. While this results in more than one database trip, it's still vastly fewer than the n+1 problem, e.g., 2 or 3 trips instead of 101, and can often be significantly more performant than a single, monstrous join for certain database systems. Preventative measures. Beware of loops. Whenever you iterate over a collection of entities that were retrieved from EF-Core, meticulously examine whether you are making additional database calls inside that loop. If you are, it's a high probability that an n+1 problem is lurking. Think about your data graph. Before you write any query, take a moment to consider all the related data you'll need for the specific operation or user interface display. Plan to load all required related information up front in your initial query. Utilize profiling tools early. Integrate database profiling into your regular development workflow. Tools provided by your specific database system, e.g., SQL Server Profiler, MySQL Workbench, or third-party ORM profilers can quickly highlight inefficient query patterns and help you catch n+1 issues long before they hit production. Anecdote case study. A mid-sized e-commerce company rolled out a new internal dashboard feature designed to give sales managers an overview of recent customer orders. Initially, the page was agonizingly slow, taking well over a minute to load for active managers. An investigation quickly revealed an egregious n+1 problem. The core query fetched 200 order records, and then, in a tightly coupled loop, each order separately made database calls to fetch its associated customer record, its shipping address, and its list of order item details. This led to hundreds of individual database calls for what should have been a single screen. By refactoring the data retrieval to use powerful include statements, all necessary customer, address, and order item data was loaded in just 1 or 2 efficient database trips. The result was dramatic. The page load time plummeted from over a minute to under 2 seconds, transforming a frustrating bottleneck into a highly productive tool. 2.2 Client-side evaluation. The hidden performance trap. While n+1 is about too many trips, client-side evaluation is about what happens during a trip, leading to fetching too much data. This pitfall can be particularly insidious because EF-Core often issues a warning, which, if ignored, can lead to severe performance issues. What it is. Client-side evaluation occurs when a part of your linq query structure is too complex or uses C# methods that EF-Core cannot translate into an equivalent SQL expression. When EF-Core encounters such an untranslatable part, it performs as much of the query as it can directly on the database server. However, it then has no choice but to pull all the relevant data that has been processed so far into your application's memory and complete the remaining filtering, sorting, or processing there on the client side, i.e., your application server. Why it's a problem. This is a significant performance bottleneck because it often leads to fetching far more data than is actually needed from the database. Instead of leveraging the database server's optimized engines to efficiently filter millions of records, your application might end up pulling entire tables or massive subsets of data over the network. This consumes vast amounts of network bandwidth, burdens your application server with high memory usage to store all that unnecessary data, and drains CPU cycles to then filter or process that data in memory. In essence, it completely negates the primary benefit of using a database, offloading mass data processing to a dedicated, highly optimized server. Example scenario. Imagine you have a large products table and you want to find products whose name contains a specific keyword. However, instead of using the standard string.contains method, you've defined a custom C hash extension method, perhaps called contains case insensitive, to perform the comparison. If you write a linq query like products where p equals p.name.contains case insensitive widget to list, EF-core will attempt to translate this, since it doesn't know how to convert contains case insensitive into standard SQL. What happens implicitly is that all products from your database table are first retrieved and streamed to your application's memory. Only then is your custom C-hash method applied to filter them down. If your products table contains hundreds of thousands or millions of records, this scenario becomes catastrophic, as your application tries to load the entire inventory into memory. How to identify EF-core warnings. This is your primary indicator. EF-core is remarkably vocal about client-side evaluation. You will almost certainly see a warning message in your application's logs, often originating from Microsoft Entity Framework Core Query. The message will explicitly state something to the effect of, the linq expression could not be translated and will be evaluated locally. Always pay close attention to these warnings. They are red flags waving furiously that indicate a potential performance disaster. Profiling tools. Observing large, unexpected data transfers from your database to your application server, coupled with sudden spikes in memory or CPU usage on your application process shortly after a database query completes, are strong indicators of client-side evaluation. Unintended materialization. Sometimes, you might inadvertently force client-side evaluation by calling to list, as enumerable, or similar methods too early in your linq query chain. These methods materialize the query results by executing the SQL generated up to that point and bringing the data into memory, meaning any subsequent filtering or processing will occur on the client side. How to fix. The core principle for fixing client-side evaluation is to ensure that as much of your query logic as possible is translated into SQL and executed directly on the database server. Rewrite to translatable constructs. Whenever a specific part of your query triggers client-side evaluation, investigate if you can rewrite that logic using C-hash constructs that EF-core can translate into SQL. For string comparisons, for example, use the standard string.contains, string starts with, or string ends with methods, as these generally have direct SQL equivalents. For more advanced or database-specific functions, like date manipulation or pattern matching, explore EF functions, which exposes common database functions that EF-core knows how to translate. In extreme cases where complex logic genuinely cannot be translated, you might consider executing raw SQL queries or stored procedures for that specific part of the operation. Materialize data strategically. If a piece of logic truly and inherently cannot be translated to SQL and must be performed in C-hash, the key is to perform an explicit to list or as enumerable call before applying that C-hash logic. This tells EF-core, okay, fetch the data processed up to this point, then I'll handle the rest in memory. The critical part here is to ensure that the data fetched before this materialization point has already been significantly filtered or reduced by other translatable query parts. For instance, you could filter by a date range directly on the database, then load only those few hundred records into memory, and then apply your custom C-hash formatting or calculations. Preventative measures. Heed EF-core warnings religiously. Make it a strict team policy to investigate and resolve every single client-side evaluation warning encountered during development. Treat them as critical, not optional. Understand translatability. Familiarize yourself with which LINQ methods, see hash constructs, and custom methods EF Core can and cannot translate to SQL. The official EF Core documentation provides a detailed list. Keep logic simple within queries. Avoid embedding overly complex custom methods, business logic, or intricate calculations directly within your LINQ query expressions that are intended for database execution. Separate the database querying from complex in-memory processing. Anecdote case study. An incredibly fast-growing e-learning platform was developing a critical daily report, Course Progress by Student. As their user base and course catalog expanded, the report generation, which used to complete in a few seconds, started taking hours and would frequently crash due to out-of-memory errors on the server. The investigative team eventually pinpointed the problem to a custom C-hash method used within the LINQ, where clause to calculate a completion percentage for each student. This was something EF Core simply couldn't convert into a SQL expression. Consequently, the application was fetching all student enrollment records and all associated course section data, massive datasets, into memory just to filter down to the few required for the report. By refactoring the logic to first use translatable queries to pull only the necessary, filtered student and course data from the database, and then calculating the completion percentage in memory, the report generation time dropped back to mere seconds, and the memory crashes ceased entirely. 2.3 Forgetting ASNO tracking. When you don't need the change tracker. One of the most potent features of EF Core is its change tracker. But like any powerful tool, it needs to be wielded with discretion. By default, when you retrieve entities using a DB context instance, EF Core meticulously starts tracking those entities. What it is? When EF Core tracks an entity, it takes a snapshot of that entity's original state, its property values, the moment it's loaded from the database. It then monitors any changes you make to that entity's properties in memory. This tracking is absolutely essential if your intention is to modify those entities and later persist those changes back to the database by invoking the Save Changes method. However, if you are retrieving data purely for read-only purposes for displaying on a web page, generating a report, or transferring to another system, and you have no intention of modifying or saving it, then the overhead associated with tracking is entirely unnecessary. The ASNO tracking method is specifically designed for these scenarios. You add it to your query to instruct EF Core not to track the entities it retrieves. Why it's a problem? Increased memory consumption. For every single entity that EF Core tracks, it maintains additional metadata and state information in memory, including a snapshot of the entity's original values. For queries that retrieve thousands or even millions of entities, common in reporting or large list displays, this extra tracking data can accumulate significantly, consuming large amounts of your application's valuable memory resources. Increased CPU usage. The change tracker isn't passive. It consumes CPU cycles. It needs processing power to take the initial snapshots of entity states, to compare current property values against those original snapshots when you modify an entity, and to manage the overall tracking process. This unnecessary work consumes valuable application resources, potentially slowing down response times, especially in high-volume applications or under heavy load. Potential for unexpected updates. If you are using a tracked entity for a read-only purpose, and it is inadvertently modified somewhere else in your application code, and later save changes, is called on the same DB context instance, EF Core might attempt to persist these unintended changes to the database. This can lead to subtle bugs, unexpected data modifications, or even errors without clear warning signs. Example scenario: consider a public-facing e-commerce website where users can browse a View All Products page. When a user navigates to this page, your application retrieves a list of product entities. These products are then displayed in a grid or list format. There is typically no intention to edit these products directly on this page. Users would go to a separate Edit Product page for that. If you simply write a query like context.productsToList, EF Core will track every single product retrieved. Even though you are just displaying them, the system is expending resources preparing for a potential save changes, which will never happen in this context. How to identify performance monitoring. If your application instances or servers exhibit unexpectedly high memory usage or CPU spikes for pages or services that primarily display or transfer data without subsequent modification, investigate whether ASNO tracking is being consistently applied in those data retrieval queries. Code review. During peer code reviews, pay close attention to queries that are fetching relatively large sets of data, especially if that data is subsequently transformed or used only for display. If the query lacks an ASNO tracking, call and there's no clear intention to modify and save the entities, it's a prime area for optimization. How to fix? The solution is straightforward. Simply append ASNO tracking to your LINQ query for any operation where you are fetching data for read-only purposes. For example, to retrieve active products for display without tracking overhead, you would write context.productsWhere P equals P is active, ASNO tracking, to list. This explicit instruction tells EF Core to fetch the active products, but to skip the resource-intensive process of tracking them for future modifications. Global default. For applications or scenarios where the vast majority of your queries are read-only, e.g., reporting services or data pipelines that primarily consume data, EF Core allows you to configure ASNO tracking as the default behavior for your DB context in its configuration. When configured this way, you would then explicitly opt in to tracking for the few queries where you do intend to modify entities using methods like ASTracking. Preventative measures. Cultivate a read-only mindset. When you are writing any data retrieval query, consciously ask yourself, am I going to modify these entities and save them back to the database after I retrieve them? If the honest answer is no, then consistently add ASNO tracking by default. Encapsulate query logic. For complex applications, consider creating dedicated methods, repositories, or query objects for read-only data access workflows. These methods can then consistently apply ASNO tracking internally, ensuring that the optimization is automatically included whenever that read-only path is taken. Anecdote case study. A popular online news portal began experiencing inexplicable, intermittent timeouts on its main article listing pages during peak traffic hours. The problem was difficult to diagnose because individual article loads were fast, but the page showing many articles would eventually fail. The issue was eventually traced back to the article retrieval queries. Developers had inadvertently omitted ASNO tracking for queries that fetched tens of thousands of article headlines and summaries for display. While the tracking overhead for a single article was negligible, the cumulative effect of tracking such a massive volume of purely read-only entities caused significant memory pressure and excessive garbage collection overhead on the web servers. This constant resource contention led to sluggishness and, eventually, server timeouts. Implementing ASNO tracking for these display-only queries dramatically reduced the application's memory footprint, sped up query execution, and completely eliminated the frustrating timeouts, restoring the portal's reliability. 2.4 Overfetching and underfetching data. The include versus select debate. Optimizing data retrieval isn't just about the number of database trips. It's also about the quantity and shape of the data you retrieve on each trip. This pitfall navigates the delicate balance between fetching too much information and fetching insufficient information. What it is? Overfetching. This occurs when your query retrieves more columns from a table or more related entities, and their properties than your application genuinely needs for a specific operation or user interface display. Underfetching. Conversely, this happens when you retrieve too little data in your initial query. This often leads to the N+1 problems we discussed earlier, where you're forced to make many subsequent database calls to get the missing pieces. It can also force EF Core into client-side evaluation if it doesn't have enough data on hand to translate a later part of your query. Include versus select. These are the two primary tools EF Core provides for loading related data, and understanding when to use each is critical. Include is used to load entire related entity objects and their entire graph, e.g., an order and all its order items, and the product details for each item. Select, often referred to as projection, is used to load only specific properties or to shape the data into a new, tailored type. Choosing judiciously between them, or even combining them, is paramount for efficient querying. Why it's a problem? Overfetching. This is wasteful on multiple fronts. It wastes database resources, CPU time and disk I/O to read unnecessary columns and rows, network bandwidth to transmit data that won't be used, and application memory to store large objects or entire related graphs that contain superfluous information. For example, if your product entity contains a large image binary, byte, or extensive text fields, like a very long description, and you're only trying to display a list of product IDs and names, fetching those large, unused fields causes unnecessary strain everywhere. Underfetching directly leads to the N+1 problem, where your application has to make many separate, inefficient trips to the database to collect the pieces of data that should have been loaded together. It can also inadvertently force client-side evaluation if you attempt to perform operations on related data that wasn't properly loaded via the database. Example scenario. Let's use our product example again. Imagine your product entity has properties like id, name, a short description, and a full-resolution image, which might be a very large byte array. Products also belong to a category entity. Overfetching example. You want to display just a list of product names and their associated category names on a product browsing grid. A query like context.products.include p=p.category to list will load the entire product object, including the large full-resolution image if it's mapped directly, and the entire category object for every product. This is overfetching because you only need a couple of properties from each. Underfetching example, leading to N+1. If you only fetch context orders to list, to display a list of orders, but later in your code, you loop through each order to display the customer name for each, you will likely trigger a separate database query for each customer if the customer entity wasn't loaded alongside the order initially. How to identify? SQL profiling. This is your best friend. Examine the actual SQL queries generated by EF-Core. Are the select statements pulling many more columns than seem necessary for the specific task? Are join operations bringing in entire related tables when only a single property or two are needed from the join table? Application memory usage. High memory consumption on your application server for pages that display lists, grids, or generate reports could be a strong indicator of overfetching, as your application is holding onto more data than it truly needs. N+1 symptoms. As discussed earlier, sluggishness, high database load, and many small, repeated queries are definitive signs of underfetching in the initial data load. How to fix? The most effective solution lies in being extremely precise about what data you instruct EF-Core to bring into your application's memory. Select for precision projection. When your specific logic or user interface only needs a subset of properties from an entity, or a few properties from related entities, or you simply want to reshape the data into a simpler data transfer object, DTO, or an anonymous type, then the select linq operator is the most efficient choice. This is often the superior approach for read-only display concerns. Example, to get just the product's ID, name, and its category's name for a list. Context.productSelect, p=new, pid, p.name, category name equals p.category.name, to list. This instructs EF-Core to generate a SQL query that selects only the id, name, and the category's name column, creating a much more efficient database query and a smaller data payload over the network. Include for graph loading when full objects are needed. Conversely, if your business logic truly requires the full entity graph, for instance, if you are retrieving an object because you intend to modify many of its properties and save changes, or if a complex validation rule needs access to all properties of multiple related entities, then include is the appropriate choice. Use it to ensure that all necessary related objects are loaded in as few database round trips as possible, without inadvertently triggering N+1 issues. Combine include and select. For specific, nuanced scenarios, you might combine these strategies. You could use include to eagerly load a related collection, e.g., an order with its order items, to avoid n+1. Then, you might apply a top-level select statement to project the entire graph into a flattened DTO structure, effectively shaping the data after it has been efficiently loaded. For instance, you could load an order including its order items, and then select the relevant properties into an order DTO that contains a simplified list of order item DTOS, effectively getting an efficient query and a clean data model for presentation. Preventative measures. Ask, what do I really need? Before you start writing any query, pause and clearly define the precise data requirements for the specific screen, report, API endpoint, or business operation you are building. Resist the temptation to take the lazy route of selecting an entire entity when only a few properties are truly necessary. Design purpose-built DTOs. Create specific data transfer objects, DTOs, for different views or operations. This practice naturally encourages you to use the select operator to populate these DTOs with only the necessary data, forcing you to think about what data is truly required. Anecdote case study. A growing company's internal inventory management system began to exhibit severe slowdowns when displaying the main product list. The page would take 30 to 45 seconds to load, even on robust servers, causing significant user frustration. The root cause was discovered to be a query that simply loaded all product entities. The product entity, unfortunately, contained two large binary fields: a small thumbnail image, a few kilobytes, and a massive full-resolution image, multiple megabytes. While the product list only intended to display product names and IDs, the query was written as a simple context.productStylist. This meant that every single product record, including its colossal full-resolution image, was being hauled out of the database and across the network, only for that specific field to be ignored by the display logic. By refactoring the query to use a select statement that only pulled ID and name from the products table, and ensuring the full resolution image was only fetched when explicitly needed on a product detail page, the list view loaded in less than a second. This fundamental shift in data access philosophy, prioritizing select over loading the entire entity, dramatically improved user experience and significantly reduced the database and network load. Chapter 3. Contextual conundrums. Managing your DB context effectively. In the world of Entity Framework Core, your DB context instance is the central gateway to your database. It's the object responsible for holding your entity models, generating queries, tracking changes, and ultimately persisting data. While simple to instantiate, its proper management, especially its lifespan and interaction with other services, is paramount to building stable, performant, and bug-free applications. Many subtle yet significant problems arise not from faulty queries or bad schema design, but from a misunderstanding of how the DB context itself should be managed. This chapter delves into the contextual conundrums, critical pitfalls related to DB context lifecycle, its integration with modern dependency injection patterns, and the complexities that arise when working with multiple contexts or encountering unexpected change tracking behaviors. Mastering these concepts is essential for moving beyond basic EF core usage to truly robust application development. 3.1. The DB context lifecycle. Short-lived versus long-lived instances. One of the most fundamental principles of DB context management is its intended lifespan. DB context instances are designed to be light and ephemeral. What it is. A DB context is meant to encapsulate a unit of work, a single atomic set of database operations. Typically, this means an instance is created, used for a specific task, like handling one web request, processing a single message from a queue, or performing a distinct background job, and then promptly disposed of. A long-lived DB context, in contrast, is an instance that persists for an extended period, perhaps across multiple, unrelated user interactions in a web application, for the entire duration of a desktop application, or even as a static or singleton object. Why it's a problem? Memory leaks. A DB context instance actively tracks all entities it loads or adds. A long-lived context will continuously accumulate these tracked entities in its memory without releasing them. Over time, this leads to a steady, unavoidable increase in your application's memory consumption, eventually causing performance degradation, garbage collection thrashing, and ultimately, out-of-memory errors or application crashes. Stale data. If data in your database changes outside the scope of a long-lived DB context, e.g., another user modifies a record or a different service updates a table, your long-lived DB context will not be aware of these external changes. It holds onto its internally cached, potentially stale, versions of entities. Subsequent queries or operations performed through this old context might retrieve or interact with outdated data, leading to logical errors, incorrect displays, or serious data integrity issues. Concurrency issues. A single DB context instance is explicitly not thread-safe. Attempting to use a long-lived context across multiple threads or concurrent requests without careful synchronization will inevitably lead to runtime exceptions, such as a second operation started on this context before a previous operation completed. Or, worse, silent data corruption due to its internal state being accessed and modified by multiple threads simultaneously. Complex conflict resolution. The change tracker accumulates more and more changes the longer a DB context lives. When save changes is finally called on a long-lived context, it might try to save many unrelated changes spanning a long period and many operations. This significantly complicates conflict resolution during concurrent updates to the same data, making debugging and error handling a nightmare. Example scenario. Imagine a simple web application where, instead of creating a new DB context for each HTTP request, a developer mistakenly created one DB context instance and stored it in a static field, making it available globally throughout the application's runtime. Or consider a desktop application that opens a single DB context at startup and keeps it open for the entire time the user interacts with it, hoping to retrieve data faster. How to identify? Steadily increasing memory usage. The most telling sign. If your application's memory footprint grows continuously during operation, not just during peak load, but over extended periods, and never stabilizes or decreases, a long-lived DB context is a prime suspect. Inconsistent data displays. Users report seeing old information on a page even after others have confirmed it's been updated. This often indicates the application is querying through a context with stale internal caches. Frequent concurrency exceptions. While DB update concurrency exception can be normal, an unusually high frequency, especially when operations seem unrelated, might point to improper context management leading to unexpected state. Runtime exceptions related to threading. Direct exceptions, explicitly stating that a second operation was attempted on the context before the first completed, are definitive indicators of thread safety violations, often stemming from long-lived contexts being implicitly shared. How to fix? The golden rule for DB context is create it, use it, and dispose of it. Dispose after use. Ensure DB context instances are properly disposed of as soon as the unit of work they represent is complete. This releases their resources, including memory. Using statement. In non-dependency injection scenarios, e.g., console applications, simple scripts, wrapping your DB context instance in a using statement guarantees it will be correctly disposed, even if errors occur. Dependency injection, recommended. In modern net applications, especially web and API, the preferred and most robust way to manage DB context lifecycle is through dependency injection, DI. Configure your DB context with a scoped lifetime. This ensures that for each incoming web request or equivalent logical operation, a fresh DB context instance is created, used, and automatically disposed when the request finishes. Preventative measures. Strict DI configuration. Always ensure your DB context is registered with a well-defined lifetime in your application's dependency injection container, almost universally scoped for web and API applications. Avoid static global contexts. Never, under any circumstances, store DB context instances in static fields, global variables, or singleton services. This pattern is a direct path to the problems described above. Educate team members. Ensure all developers working on the project understand the ephemeral nature of DB context and the implications of its life cycle. This knowledge is crucial for preventing these issues from being introduced. Anecdote case study. A fast-growing public-facing web API backend began exhibiting alarming symptoms. Under moderate load, its memory usage would steadily climb, never releasing, until the entire API application would crash. After hours of debugging, the team discovered a subtle configuration bug. The DB context had accidentally been registered as a singleton service in the application's startup. This meant every single API request, over tens of thousands of requests per hour, was using the same DB context instance, causing it to endlessly accumulate tracked entities and associated metadata. The fix was a single-line change in the DI configuration, setting it to the appropriate and default scoped lifetime. Instantly, the memory leaks vanished, and the API became stable and performant under heavy traffic, proving how a small lifecycle misstep can have catastrophic effects at scale. 3.2 Misconfiguring dependency injection. The scoped lifetime imperative. Following on from the previous section, if dependency injection is your chosen method for managing DB context, which it almost certainly should be in modern net, then correctly configuring its lifetime is paramount. The default scoped lifetime is nearly always the right choice, and deviating from it can lead to subtle yet significant problems. What it is? Dependency injection, DI, allows for the automatic creation and provision of service instances your application needs. When you add your DB context to the DI container, you specify its intended lifetime. Singleton. A single instance is created for the entire lifetime of the application. Scoped. A new instance is created for each defined scope, e.g., per HTTP request in a web application or per message in a message processing service. Transient. A new instance is created every single time it is requested. For a DB context, the scoped lifetime is the almost universally recommended and default setting. This ensures that a fresh DB context is available for a complete, isolated unit of work, and that the same DB context instance is reused within that single unit of work, e.g., across multiple services being called within one web request. Why it's a problem? Incorrect lifetime, singleton. Registering your DB context as a singleton, e.g., services add DB context, my DB context, lifetime. Service lifetime singleton introduces all the classic problems of a manually long-lived context discussed in section 3.1. Incessant memory accumulation, stale data, and severe thread safety violations when multiple requests try to use the same singleton instance concurrently. Incorrect lifetime transient. While perhaps seemingly less harmful than singleton, registering DB context as transient, e.g., services add DB context, my DB context, lifetime. Service lifetime transient can also lead to issues. If various services within the same logical operation, e.g., a web request where one service calls another, and both depend on my DB context, each request a DB context instance, they will each receive their own distinct DB context instance. Each of these distinct contexts will have its own independent change tracker. This means entities loaded by one transient context will not be tracked by another, potentially leading to lost updates. If an entity is modified by one context, but save changes is called on another that doesn't know about it, or inefficient database operations, e.g., trying to add an entity that's already effectively seen by a different, unnoticed context. Furthermore, managing transactional boundaries becomes much harder, as calling save changes on one transient context doesn't affect another. Thread safety misconception. Regardless of the DI lifetime, a single DB context instance is never thread safe for concurrent access. Even with a scoped lifetime, if you explicitly spin up new threads within a single request and share that scoped DB context instance across them without proper synchronization, you will encounter exceptions or corrupted state. The scoped lifetime primarily helps prevent accidental multithreading issues within the web request processing pipeline by providing a dedicated instance per request, but explicit multi-threading still requires careful DB context management, usually by ensuring each thread gets its own independent DB context instance. Example scenario: a developer, unfamiliar with DB context best practices or DI lifetimes, might mistakenly configure their DB context as a singleton in Startup CS or Program CS in newer net versions. Or, less commonly, they might explicitly set it to transient when they should have relied on the default scoped behavior. How to identify application crash hang. If multiple users or concurrent operations cause your application to crash or become unresponsive, especially with direct exceptions related to second operations started, it's a strong indicator of a DB context being used concurrently or globally when it shouldn't. Inconsistent transactional behavior. If seemingly related database updates fail to commit atomically or changes seemingly disappear, it might be due to multiple transient DB context instances within the same logical operation, each managing its own unit of work separately. DI container analysis. A direct check of your startup CS/program CS file or other DI configuration to see how your DB context is registered is the most straightforward way to identify an incorrect lifetime configuration. How to fix: always use scoped lifetime, default. The simplest and most consistent fix is to always register your DB context using its default scoped lifetime. When you call services add DB context my DB context, options equals /configuration, the lifetime is already scoped by default. Explicitly setting lifetime. Service lifetime scoped is redundant but harmless. Avoid singleton and transient unless you have an extremely specific, well-understood, and niche reason to do so, and you are prepared to handle the consequences. Isolate DB context usage in threads. If you find yourself in a scenario where you absolutely must perform database operations across multiple threads, e.g., in a background job or complex parallel processing, do not share a single DB context instance. Instead, ensure each thread or asynchronous unit of work gets its own independent DB context instance. This is typically achieved by creating a new iService scope for each separate unit of work, and then resolving a DB context from that new scope. Preventative measures. Adherence to best practices. This is one of those areas where following the standard prescribed DI setup for EF Core is not just good practice, but critical for stability and performance. Understanding lifetimes. Ensure that developers, particularly those new to net core or dependency injection, thoroughly understand the implications of singleton, scoped, and transient lifetimes, especially in the context of stateful objects like DB context. Anecdote case study. An incredibly frustrating bug plagued a new feature in a NetCore background worker service. The service would process large batches of customer orders, and internally, it sometimes needed to update several related entities, e.g., order, customer, inventory. Despite trying to wrap operations in transactions, updates would sometimes fail to save, or only partial changes would commit. The core issue was that the DB context was registered with a transient lifetime. This meant that each time a specific helper service was invoked within the order processing pipeline, it would get a brand new, distinct DB context instance, even if it was part of the same overall order processing operation. As a result, one part of the code might update the order entity on DB context A, while another part updated inventory on DB context B. When DB context A save changes was called, DB context B tickets changes were unknown to it, and vice versa. By simply changing the DB context registration from transient to the default scoped lifetime, all parts of the order processing within a single background job instance subsequently operated on the same DB context, allowing changes to be tracked and committed atomically, resolving the issue entirely. 3.3. Working with multiple DB contexts in a single application. As applications grow in complexity, it's not uncommon to encounter scenarios where you need to interact with multiple databases or even distinct schemas within the same database, each managed by its own dedicated DB context type. This modularization can be beneficial, but it introduces its own set of contextual conundrums. What it is. In larger systems, particularly those moving towards microservices, or those that need to integrate with legacy databases alongside new ones, you might define and use several different DB context types. For example, order DB context might manage order-related tables, while customer DB context handles customer data, potentially residing in completely separate physical databases. Why it's a problem. Entity instance isolation. Each DB context instance has its own, completely isolated change tracker. An entity instance loaded or tracked by DB context A cannot be directly manipulated or saved by DB context B. Trying to attach an entity that was originally loaded by context A to context B often results in a runtime error. Specifically, an invalid operation exception stating, the instance of entity type X cannot be tracked because another instance with the same key value for type X is already being tracked. This fundamental isolation means you cannot simply pass an entity loaded from one database to a service connected to a different database and expect it to automatically track or save changes. Transaction management complexity. Coordinating atomic transactions across multiple distinct DB context instances, and thus potentially multiple physical databases, is significantly more complex than a single DB context. Simple save changes. Calls on separate contexts do not form a single atomic transaction. Achieving true atomicity across databases typically requires explicit distributed transaction managers, like System Transactions Transaction Scope in environments where Distributed Transaction Coordinator, or DTC, is configured, or manual XA transactions for databases that support it. These add architectural complexity, configuration headaches, and operational overhead, and are often avoided in favor of eventual consistency models in modern distributed systems. Confusing entity identity. If you inadvertently define two distinct DB context types that happen to map to the same C-hash entity class, e.g., both sales DB context and support DB context have a DB set customer, it can lead to confusion about which DB context should be used for which operation. More importantly, it reinforces the problem of shared entity instances, where a customer object retrieved from sales DB context is fundamentally different in terms of its tracking by EF core than a customer object retrieved from support DB context, even if they represent the same underlying database record. Example scenario: a company migrating from an old monolithic application to a new microservices architecture. The existing customer's data resides in a legacy database accessed by legacy customer DB context, while new order data is stored in a modern database accessed by new order DB context. A new service needs to process an order and also update a customer's last order date field. How to identify explicit exception messages. EF core is generally quite clear about tracking conflicts. You will encounter explicit invalid operation exception messages mentioning the instance of entity type X cannot be tracked because another instance with the same key value for type X is already being tracked, indicating an entity loaded by one context is being passed to another. Lost updates / data inconsistency across systems. If data changes made in one part of your application don't seem to propagate to another part that uses a different DB context, or if operations requiring updates across both databases are not atomic, e.g., an order is placed, but the customer's last order date isn't updated, it points to incorrect cross-context handling. Difficulty with transactions. Recognizing that simple save changes calls aren't providing the atomicity you need across different data stores means you're bumping into the distributed transaction challenge. How to fix. The key principle here is understanding that entity instances are owned by the DB context that loaded or attached them. Entity identity within a context. Reinforce the understanding that an entity instance's identity, especially concerning change tracking, is tied to the specific DB context instance that loaded or attached it. A C-hash object customer A loaded by sales DB context is distinct in EF cores eyes from customer B loaded by support DB context, even if customer A id equals customer B id. Data transfer, detach, reattach carefully. If you must move an entity's data from one DB context tracking to another, you cannot simply pass the entity object directly. You must explicitly detach it from the first context, e.g., using context entry entity state equals entity state dot detached, and then attach it to the second context. This is a complex operation that demands meticulous understanding of entity state values, added, modified, deleted, unchanged, detached, to ensure the entity is reattached with the correct state. Often, it is much simpler and safer to query fresh data from the target DB context, or, even better, map the data from the source entity to a simple DTO, and then use that DTO to hydrate a new entity instance for the target context to track. This transfer via DTO pattern avoids all tracking conflicts, distributed transactions, or eventual consistency. For operations that absolutely must modify data atomically across different databases, you will need to implement distributed transactions, transaction scope where supported and configured, or manual cross-database transactional logic. However, consider if eventual consistency is acceptable. This pattern involves performing local transactions on each database and using messaging queues or other mechanisms to ensure all related updates eventually complete, even if not simultaneously. This is often simpler and more scalable in distributed systems. Preventative measures, clear architectural boundaries. Design your application, especially in a microservices context, so that a specific business operation predominantly uses only one DB context instance and its associated data model. This keeps concerns separated. Avoid entity sharing across contexts. Make it a strict policy. Do not pass entity objects loaded by one DB context into methods or services that internally use a different DB context to perform updates on those exact entity instances. Instead, pass plain data structures, DTOs, that can then be rehydrated or used to update entities within the target context. Isolate cross-context operations. If operations must span multiple DB context instances, encapsulate this complexity carefully. Implement clear boundary patterns and explicitly manage transactional guarantees. Anecdote case study. A development team building an internal management system faced constant headaches during data migration. They had a legacy patient database and a new, modernized one. Their migration tool would pull a patient record from the legacy patient DB context, make some data corrections, and then attempt to save it into the new patient DB context using the add or update methods. Time and again, they encountered the instance of entity type patient cannot be tracked because another instance with the same key value for type patient is already being tracked, exception. The team was mystified, not understanding that the patient entity instance they held was already associated with the legacy patient DB context's change tracker. The solution involved explicitly detaching the patient entity from the legacy context immediately after retrieving it, then attaching it to the new context with the appropriate state. Or, more simply, projecting the data from the legacy patient into a patient DTO, and then creating a new patient entity instance for the new patient DB context to track and save. The latter approach proved far more robust and less error-prone. 3.4 Misunderstood change tracking behavior. Advanced topics. While we touched on as-no tracking. In Chapter 2, to avoid unnecessary tracking, the DB context's change tracker also possesses deeper complexities and subtle behaviors that, if not fully understood, can lead to perplexing bugs, data inconsistencies, or unexpected query results. What it is, the change tracker is the sophisticated engine within DB context that monitors the state of entities. When you retrieve an entity without as-no tracking, or add one, EF-core begins tracking it. This tracking involves maintaining the entity's original values, its current values, and its entity state. Think of it as a status. Added, modified, deleted, unchanged, detached. Beyond these basics, specific behaviors can cause confusion. Automatic merging identity resolution. If the DB context's change tracker is already tracking an entity with a specific primary key, and you attempt to attach, add, or even load another instance of the same entity type with the same key, EF-core will prioritize the already tracked instance. It will often throw an exception if the new instance is different in some way, or it might silently merge changes, leading to unexpected behavior. State-machine transitions. The interaction of methods like add, update, attach, and remove with an entity's entity state can be intricate. For example, add marks an entity as added. Update generally scans properties and marks the entity as modified if properties have changed, but it will mark an untracked entity as modified. Attach changes an untracked entity to unchanged. Incorrectly applying these methods can lead to entities not being saved, or being saved with the wrong type of SQL command, e.g., an insert instead of an update. Relationship fix-up. A subtle but powerful feature. When you load entities into a DB context instance, EF Core can automatically fix up relationships between them in memory if they were loaded in the same DB context instance, even if you didn't explicitly include the related navigation property. This means if you load an order and then separately load the customer associated with that order, EF Core will link them together in memory. This can occasionally lead to unexpected navigation property population. Shadow properties. These are properties that exist as part of your EF Core model and are mapped to database columns, but they do not exist as properties on your actual C-hash entity class. They are managed internally by EF Core and have their own change tracking behavior. Why it's a problem? Data loss or incorrect updates. Misunderstanding how EF Core resolves identity and handles state transitions can lead to modifications not being saved, or, more insidiously, incorrect changes being overwritten silently by the change tracker's internal logic. Unexpected invalid operation exception. Trying to attach or update entities with incorrect assumptions about their current tracking state frequently results in invalid operation exception or similar errors related to primary keys already being tracked. Debugging difficulty. Bugs stemming from subtle change tracker behavior are notoriously hard to diagnose. The symptoms can be elusive. Why didn't this update save? Or, why did this related object suddenly appear? Example scenario. Disconnected entity updates. A common scenario in web APIs. A client sends a JSON payload representing an updated product object. Your API typically gets this detached product object. If you then simply try context.productsUpdate, product from client, and in product with that ID is already tracked by the DB context for that request, perhaps loaded in a validation step, EF Core will throw an exception. A novice might then use attach followed by marking some properties as modified, which can be brittle. Relationship fix-up surprise, you load a specific customer by ID. Later in the same DB context instance, you load an order for that customer without explicitly using include O equals O customer. You then find that the order customer navigation property is unexpectedly populated, even though you didn't include it. While often a helpful feature, if misunderstood, it can lead to confusion about what data you actually loaded from the database. How to fix? The solution lies in a deep and deliberate understanding of the change tracker's mechanisms. Explicitly understand and set entity state for disconnected entities. When you receive an entity object that was not loaded by the current DB context, i.e., it's a disconnected entity common with API inputs, you must explicitly tell EF Core its intended entity state before calling save changes. For new entities, context add entity sets entity state added. For entirely updated entities, context update entity sets entity state modified and marks all scalar properties as modified. This method is tricky when the entity might already be tracked or part of a complex graph. For existing entities where you only change some properties, first load the original entity from the database within the current DB context. var existing entity equals context entities find entity ID. Then, apply the changes from your disconnected entity to this tracked existing entity, e.g., manually assign properties or use a mapping library. Finally, call context save changes. This is the safest pattern for updates. For deletion, context remove entity sets entity state.deleted. If the entity wasn't already tracked, remove will first attach it in unchanged state, then mark it deleted. Attach versus update nuances. Attach entity simply tells EF Core to start tracking entity in the unchanged state, assuming it already exists in the database and hasn't changed. Update entity tells EF Core to track entity and mark it as modified. Be cautious when updating an entity that might already be tracked. The best, most explicit way is usually to load the existing entity and apply changes. Find versus first or default. Remember that context entities find, primary key, first checks the DB context's local change tracker cache for an entity with that primary key before querying the database. If it finds it in the local cache, it returns the tracked instance, avoiding a database trip. First or default, however, always constructs a query and hits the database if the entity is not already loaded as part of a previous query that used as tracking. Understanding this distinction can avoid unnecessary database calls and tracking conflicts. Change tracker operations. For advanced scenarios, properties on context change tracker can be useful, such as entries, to inspect all tracked entities or clear, to detach all currently tracked entities, use with extreme caution as it clears the entire session. Preventative measures. Adopt load modify save pattern for updates. For API updates or disconnected entity scenarios, adopt the highly recommended pattern. Load the original entity from the database within the current DB context scope. Apply changes from the client-provided DTO object to that tracked entity, call save changes. This inherently handles existing tracking and correctly identifies modified properties. Thoroughly test disconnected scenarios. Any part of your application that takes entity data from outside the current DB context's lifespan, e.g., from a web client or a message queue payload, and attempts to reintegrate it for saving needs rigorous testing to ensure it correctly manages entity state. Leverage AutoMapper or similar. Tools like AutoMapper can help automate the process of mapping a client-provided DTO to a loaded, tracked entity, simplifying the apply changes step. Anecdote case study. A critical issue arose in a SaaS product's public-facing API. Clients would send updated user objects, but occasionally, the API would return a cryptic, already tracked, invalid operation exception when trying to save. The backend user update endpoint was configured to simply call context.usersUpdate, user object from client. However, there was a middleware component that, for logging and auditing, would first independently load the user from the database. When the update endpoint later received the user object from client and tried to update it, if the logging middleware had already loaded that same user ID, the DB context was already tracking an instance with that ID. EF Core threw the exception, preventing the update. The fix involved changing the update endpoint to retrieve the user from the database first, using context.usersFind, user object from client ID, then applying the changes from user object from client to this tracked entity, and finally calling save changes. This pattern ensured that update was never called on a potentially duplicate entity instance, elegantly resolving the complex tracking conflict. Chapter 4. Mapping Mayhem. Designing your model for success. At the heart of object relational mapping, ORM, lies the concept of a map. The intricate blueprint that defines how your C# classes and their properties translate to tables and columns in your relational database. While Entity Framework Core excels at inferring much of this mapping by convention, relying solely on defaults can lead to subtle yet significant mapping mayhem. Improperly designed or configured models can result in a wide array of problems, from performance bottlenecks and data integrity issues to confusing code and difficult debugging. This chapter explores common pitfalls related to EF Core's mapping capabilities. We'll examine how mistakes in defining your entities, relationships, and property configurations can undermine your application's reliability and maintainability. Mastering model design is crucial for harnessing EF Core's full power and building a robust data layer. 4.1 Schema Mapping Struggles. When conventions fall short, EF Core uses a powerful set of conventions to automatically map your C# classes to database structures. For instance, a class named product will typically map to a table named products, and a property named id or product ID will be assumed to be the primary key. However, these conventions aren't always enough, or they might even lead you astray if your database schema or naming conventions differ. what it is. This pitfall arises when the default assumptions EF Core makes about your model don't align with your actual database design or your desired behavior. This includes incorrect table names, column types, or misinterpretations of primary keys. Why it's a problem: failed database operations. If EF Core tries to generate SQL for a table or column that effectively doesn't exist, because it's named differently, your application will crash with runtime exceptions. For example, a SQL error indicating an invalid object name. Data type mismatches. EF Core might map a C-hash string property to a default nvarchar max database column when a varchar 255 or nvarchar 50 would be more appropriate and efficient for the specific data. Or it might map a C-hash date time to a database type without considering time zone requirements, leading to subtle data corruption. Performance bottlenecks. Inefficient data types, e.g., using max lengths where shorter are sufficient, or incorrect indexing due to misunderstood mappings, can severely impact query performance. Schema drift errors. EF Core's migrations will attempt to create or modify your database schema based on its interpretation of your model. If this interpretation is wrong, you'll end up with incorrect database structures that don't match your intentions. Example scenario: your existing database has a table named customers data, plural, and includes data, while your C-hash class is simply customer. EF Core's default convention would look for a customer's table, leading to errors. You have a C-hash string property called code, which should store a fixed-length 5-character product code. EF Core, by default, will map this to nvarchar max, using excessive storage and potentially less efficient indexing than a precise char 5 or nvarchar 5. How to identify runtime exceptions. The most obvious sign is SQL exception or similar errors indicating that a table or column could not be found or that a data type conversion failed. Generated migrations. Review the SQL that EF Core generates in migration files. If you see create table or alter table statements with unexpected names, incorrect data types, or missing constraints, your mapping is likely off. Database schema review. Compare the actual database schema using a tool like SQL Server Management Studio or dbeaver against your C-hash model definitions. Look for discrepancies in names, types, and constraints. How to fix data annotations. For simple overrides, you can use attributes directly on your C-hash entity classes and properties. For example, table, customers data, on your customer class or column, product code, type name equals char 5 on your code property. Fluent API recommended for complex mappings. For more robust and cleaner configuration, use the Fluent API in your DB context's on-model creating method. This allows you to centralize your mapping logic and avoids cluttering your entity classes with EF Core-specific attributes. For example, model builder entity customer to table, customers data, or model builder entity product. Property p=p.code has column name, product code, has column type, char 5, custom conventions. For highly customized naming rules across your entire application, you can even implement custom conventions, though this is more advanced and less commonly needed for basic mapping issues. Preventative measures. Early schema alignment. If working with an existing database, meticulously map your C-hash entities to the actual schema from the start. Don't assume conventions will always match. Review migrations. Always review the SQL generated by EF Core migrations before applying them to a production database. This is your last line of defense against incorrect schema updates. Be explicit. When conventions don't perfectly align, or when you need stricter data type definitions, be explicit with column attributes or Fluent API configurations. Anecdote case study. A development team was porting a legacy ASP.NET application to NetCore with EF Core. The old database used a peculiar naming convention. All primary keys were named ID, all caps, regardless of the table. Their user entity had a property userid, and by default, EF Core mapped this to a column userid. When they tried to run the application, it crashed with a SQL error: invalid column name userid. The fix was simple but required understanding the mapping, adding column, ID, to every primary key property in their entities, or more cleanly, using Fluent API. Model builder entity user. Property, u equals u.user ID, has column name, d. This small mapping tweak, applied systematically, resolved a blocking issue that initially seemed complex due to its systemic nature across many tables. 4.2 Relationship riddles. Misconfigured one-to-many and many-to-many. Relationships between entities are the backbone of any relational database. While EF Core often infers relationships, explicit configuration is crucial for correct behavior, especially when conventions aren't followed or when you need more control. Misconfiguring relationships is a prime source of frustration and bugs. What it is? This pitfall involves incorrect or ambiguous definitions of how your entities relate to each other, such as missing or wrongly specified navigation properties, e.g., a customer object not having a collection of orders. Incorrect foreign key properties, e.g., naming a foreign key customerid when the convention expects customerid. Ambiguous relationships, e.g., two one-to-many relationships pointing to the same foreign key, or a many-to-many without a clear join table. Ignoring required versus. Optional relationships, e.g., where a foreign key can be null, but EF Core assumes it's always required. Why it's a problem? N+1 problems. If relationships aren't configured correctly, EF Core might not be able to generate efficient join-s for eager loading, leading to the N+1 problem, as discussed in Chapter 2. Data integrity failures. Incorrectly specified required foreign keys can lead to DB update exception when saving, or allow invalid data to be inserted if the database doesn't enforce the constraint and EF Core doesn't understand it. Broken navigation. You won't be able to easily traverse your object graph, e.g., customer orders might be null or empty when it shouldn't be, because EF Core doesn't know how to link the entities. Confusing data states. Entities might be saved, but their relationships might not be correctly established in the database, leading to orphan records or incomplete data. Migration errors. EF Core might generate incorrect foreign key constraints or even fail to create them during migrations. Example scenario. You have order and customer entities in a one-to-many relationship. Customer has many orders. You forget to include a customerid foreign key property on your order entity, relying solely on a navigation property. EF Core might infer a foreign key name that doesn't match your database. You have a book and author in a many-to-many relationship. You omit creating an explicit book author join entity, expecting EF Core to handle the hidden join table by convention, but miss a configuration step for how two book objects can relate to author objects. How to identify. SQL in migrations. Examine the create table and alter table statements in your migrations. Are foreign key constraints created with the correct names and ON delete behaviors? Do the relationships look as expected? Testing data loading. Write integration tests where you load an entity and then try to access its related entities, e.g., load a customer and iterate through customer orders. If they are unexpectedly empty or throw exceptions, the relationship might be misconfigured. DB update exception on save. If you get exceptions during save changes related to foreign key constraints or nullability violations, e.g., cannot insert null into column, customerid, it often points to a relationship mapping issue. How to fix. Fluent API is the most powerful and explicit way to configure relationships. One-to-many, use has one, with many, and has foreign key. Example, model builder entity order, has one O equals O customer, with many C equals C orders, has foreign key O equals O customerid. This clearly defines the relationship and the foreign key property. One-to-one, use has one and with one. Example, model builder entity user, has one U equals U dot user profile, with one up equals up dot user, has foreign key user profile up equals up dot userid. Many-to-many with join entity. Best practice is to define an explicit join entity. Configure two one-to-many relationships from the join entity to the two main entities. Example, model builder entity book author, has one ba equals ba book, with many B equals B book authors, has foreign key ba equals ba bookid, and similarly for author. Required versus optional. Use is required, or is required false on the foreign key property to control nullability. For example, model builder entity order. Property O equals O customer IDs is required. Preventative measures. Explicit relationship configuration. For any relationship beyond the simplest, most conventional one-to-many, use Fluent API. It forces clarity and reduces ambiguity. Follow naming conventions. Sticking to standard foreign key naming conventions, target entity name ID, for example, reduces the need for explicit mapping. Cascade delete behavior. Be explicit about onDelete. Behavior, e.g., delete behavior.cascade, delete behavior set null, delete behavior restrict, to prevent accidental data loss or unexpected errors. Anecdote case study. A complex project involving hierarchical data, categories and subcategories, struggled with data fetching. They had a category entity with a parent category id property and a navigation property parent category. When trying to load a category and its parent, the parent category property was always null, even if parent category id had a value. It turned out they had defined hasMany where they should have used hasOne. Model builder entity category. HasMany, C equals C parent category, with one C equals C children. This made no sense semantically. The fix involved correctly identifying it as a hasOne relationship from category to its parent category and a withMany relationship from a parent category to its children categories. Model builder entity category. Has1 C equals C parent category, with many C equals C children. Has foreign key C equals C parent category id. This correct configuration immediately enabled proper navigation and eager loading of the parent-child hierarchy. 4.3 Navigating key nuances. Primary key and foreign key issues. Primary and foreign keys are the cornerstones of relational databases. While EF Core often handles them seamlessly, misunderstandings about their properties and interactions can lead to fundamental data problems. What it is? This pitfall revolves around subtle issues with key definitions. Incorrect primary key definition. EF Core might not correctly identify your primary key if it's not named id or entity name ID, or if it's a composite key, multiple properties forming the key, not explicitly configured. Auto-generated keys. Misunderstanding how identity columns, auto-incrementing keys, work, especially with composite keys or when using GUIDs. Foreign key constraint violations. Not properly understanding when EF Core will enforce foreign key constraints or not configuring onDelete actions correctly. Using find versus querying. Misunderstanding how find uses the primary key and the change tracker can lead to surprising behavior compared to standard LINQ queries. Why it's a problem? Failed saves updates. Operations that rely on knowing the primary key for updates, e.g., update, remove, will fail or operate incorrectly if the key is not recognized. Duplicate data. If your primary key is not enforced or not unique, you can easily insert duplicate records, leading to data integrity issues. Orphaned records. Incorrect foreign key configurations, especially onDelete rules, can leave child records without a parent when a parent is deleted, leading to inconsistent data. Performance issues. Database operations are heavily optimized around primary and foreign key indexes. If EF Core builds inaccurate queries due to misconfigured keys, performance suffers. Example scenario. You have an entity order line with a composite primary key consisting of orderid and productid. You forget to configure this as a composite key. EF Core will try to find a single id property or infer one, fail, and you won't be able to save or retrieve order line entities correctly. You are using GUIDs for primary keys, but your C hash code manually assigns them only for new entities, leading to duplicate key errors when EF Core tries to reinsert them because it assumes they are managed by the database. How to identify exceptions on save changes. DB update exception explicitly referencing duplicate primary key or foreign key constraint violation errors are direct indicators. Incorrect SQL in migrations. Look at primary key and foreign key clauses in your generated migration SQL. Are they correct? Do they include all the properties you expect, unexpected null or default values? If a foreign key property that should have a value is null after saving, the relationship or key configuration might be at fault. How to fix? Fluent API provides precise control over key definitions. Single primary key. By convention, a property named id or entity name ID will be the primary key. If it's different, use entity has key, e equals my custom key property. Composite primary key. Specify all properties forming the key in the has key method. Model builder entity order line. Has key, all equals new, all order ID, all dot producted. Identity, auto-generated versus custom keys. For integer primary keys, EF core assumes they are database-generated identity columns. You can explicitly set this using value generated on add. For GUIDs, value generated on add will instruct EF core to generate the GUID client side before insertion. If your database generates GUIDs, use value generated on add, has default value SQL, NUID, for SQL Server. If you always supply the key, use value generated never. Foreign key indexing. While EF core adds indexes on foreign keys by default, you can explicitly add them using hasIndex for performance fine-tuning. Preventative measures. Clear key strategy. Decide upfront on your primary key strategy, integers, GUIDs, natural keys, composite keys, and stick to it, configuring it explicitly in on-model creating. Validate identity generation. Always verify that key generation, client-side or database-side, aligns with your expectations. Test key-based operations thoroughly. Ensure that saving, updating, and deleting entities by their keys works correctly for all your entities, especially those with composite keys. Anecdote case study. An application had invoice and invoice line item entities. The invoice line item had a composite primary key, invoiced, foreign key, and sequence number. The developers forgot to configure this composite key. When they tried to add multiple invoice line item objects to a single invoice and save them, only the first invoice line item would save successfully. Subsequent attempts for the same invoice with different sequence numbers would silently fail, and only the initially saved item would be retrieved from the database later. The DB context's change tracker would treat later invoice line item instances as duplicates of the first one because it only recognized invoiced as a key, not the full composite. The fix was to explicitly define the composite key. Model builder entity invoice line item has key, li equals new, li.invoiced, li sequence number. Once applied, all line items saved and retrieved correctly, clarifying the entity's identity to EF core. 4.4 Shadow Properties, the unseen dangers. Shadow properties are a powerful but non-obvious feature of EF core. They allow you to define properties that exist in your EF core model and map to database columns, but are not exposed as properties on your actual C# entity class. They can be useful, but their invisible nature can lead to confusion and unintended behaviors if not managed carefully. What it is? A shadow property is a property that is part of your EF core entity model, but does not correspond to a property in your C# class. You configure them via the Fluent API. EF core tracks their values and generates SQL for them just like regular properties. They are often used for foreign key properties that you don't want to expose directly on your principal entity, or for auditing fields like created on or last modified on that are managed entirely by the data layer. Why it's a problem? Debugging difficulty. Because a shadow property isn't directly on your C# class, its value isn't immediately visible during debugging, making it harder to track state changes or understand why certain database operations are occurring. Accidental null values. If a shadow property is meant to be set programmatically, e.g., an audit timestamp, but the logic to set it is missing or flawed, it can go unnoticed until a database not null constraint error arises during save changes. Unintended data overwrites. If you're manually managing the value of a shadow property, but then load an entity and save it without updating that specific shadow property, its value will retain the database's original value rather than being explicitly set prior to saving, which might not be the desired behavior for an internal audit field that changes on update. Confusing save behavior. When save changes is called, EF core checks all properties, including shadow ones. If a shadow property's value has changed according to the change tracker, it will be included in the update statement, even if you never directly interacted with it in your C# code. Example scenario. You use a shadow property for last updated date on all your entities. You have a mechanism in your DB context to set this on save changes. However, a developer accidentally calls update entity for an entity that wasn't being tracked, then sets some properties and then saves. The last updated date shadow property might not be correctly updated unless the change tracking mechanism is robust. A foreign key is implemented as a shadow property. Debugging a relationship issue, a developer struggles to confirm if the foreign key value is correctly set because it's not directly accessible on the C# entity. How to identify? DB update exception related to nullability. If a not null constraint exception occurs on a column that doesn't correspond to a C# property, it's likely a shadow property that wasn't correctly assigned a value. Unexpected update clause in SQL. If you're profiling SQL and see a column being updated when you didn't explicitly touch a corresponding C# property, it could be a shadow property. Debugging sessions. Developers might notice that audit fields in the database don't update as expected, even though no explicit C# properties for them exist. How to fix? Careful design. Only use shadow properties when their hidden nature genuinely simplifies your C# model, e.g., for purely internal EF core foreign keys or audit fields set by database events. Access via entry. You can access and set shadow property values using the entry method on your DB context. var entry equals context entry entity, entry.property, my shadow property, current value equals some value. Centralized logic. Implement logic for shadow properties, like audit timestamps, in a single, reusable place, often by overriding save changes, in your DB context or using interceptors. This ensures consistency and reduces errors. Preventative measures. Documentation. If you use shadow properties, document their existence and purpose clearly within your codebase, e.g., in a comment on the onModel creating method. Custom audit interfaces alternative. For audit fields, consider creating a C# interface, e.g., iAuditable, that defines created on and last modified on properties. Then implement these properties directly on your entities and populate them via an interceptor or overridden save changes method. This makes the audit fields visible on the C# entity and debuggable. Avoid overuse. Don't use shadow properties just to reduce clutter in your C# model if their direct exposure would clarify behavior. Anecdote case study. In a multi-tenant application, a tenanted shadow property was used on almost every entity to ensure data isolation. The tenanted was automatically set by an save changes override in the DB context. However, a new developer, when debugging a data saving issue, found it extremely difficult to trace why certain records were appearing under the wrong tenant, or not at all. The tenanted wasn't visible on the entity, and they didn't know to check the entry, property, tenant ID, current value. The solution was to make the tenanted a regular, albeit read-only, C# property on the base entity common to all tenants. This instantly made the tenant ID visible in debugging and allowed for better programmatic control and validation, drastically reducing future tenant data isolation issues caused by misunderstanding the shadow property. 4.5 Value conversion conundrums, bridging type gaps. EF Core allows you to convert values between your C# type and the database type. This is incredibly powerful for mapping complex C# objects, like enums, GIDs, or custom value objects, to simpler database columns, like integers or strings. However, misconfigured or misunderstood value conversions can lead to data saving issues or unexpected query behavior. What it is? A value converter allows you to specify how a property's value should be converted when reading from or writing to the database. For example, converting a C# order status enum, e.g., pending shipped to an int 0, 1 in the database, or perhaps to a string pending shipped. Why it's a problem? Failed conversions. If the conversion logic is flawed, or if data in the database doesn't conform to what the converter expects, you'll encounter runtime exceptions during data retrieval or saving. Performance impact. overly complex or inefficient value converters can marginally impact performance, especially if applied to frequently accessed properties on large result sets. Query translation issues. EF Core must be able to translate your LINQ queries involving properties with value converters into appropriate SQL. If your converter is too complex or involves C-hash logic that EF Core can't translate, you'll either get a runtime error or trigger client-side evaluation, as discussed in Chapter 2. Data consistency problems. If you have different conversion logic for the same C-hash type in different DB contexts or projects, it can lead to inconsistent data interpretation. Example scenario. You store an order status enum in your database as a string, e.g., pending, shipped. Your enum might have new values added later, e.g., canceled. If your converter doesn't handle the conversion of the C-hash enum to the string representation correctly, or if old string values from the database don't map to new enum members, you'll get errors. You use a complex custom class for an address, e.g., address class with street, city, zip, and want to store it as a single JSON string column in the database using a value converter. Queries filtering by city would likely not be translatable to SQL and would force client-side evaluation. How to identify invalid cast exception or format exceptions. These are common when data read from the database cannot be converted into your C-hash type, or vice versa during saving. Client-side evaluation warnings. As discussed in Chapter 2, if your LINQ queries involving a converted property result in client-side evaluation warnings, it means EF Core cannot translate the conversion logic to SQL. Data inconsistencies. If data appears correctly in one part of your application but incorrectly when viewed directly in the database, a conversion issue is a strong suspect. How to fix. Fluent API for has conversion. Use has conversion in on-model creating to define your converters. For enums, EF Core 5 Plus offers built-in support for string conversions without needing a custom converter. Simple converters. Keep converters as simple as possible. Ideally, they should only map between primitive types int, string, and your C-hash type. For complex object serialization to JSON strings, ensure you understand the query limitations. Ensure bidirectional translation. Test both read database to C and write C-hash to database paths for your converters. Handle nulls. Ensure your converters gracefully handle null values if the database column is nullable. Preventative measures. Prioritize translatability. Before implementing a complex value converter, consider if the desired querying behavior will be possible in SQL. If you need to query based on properties of the converted C-hash object, it might be better to store those properties as separate columns in the database. Robust enum handling. When converting enums, consider storing them as integers, their underlying value, if possible for better performance and query translation. If string conversion is necessary, ensure new enum values are handled during database reads, e.g., by providing a default unknown value. Test edge cases. Test your converters with edge cases, including nulls, boundary values, and new-old data formats if doing data migration. Anecdote case study. A company building a survey application used a custom choice enum for survey responses, e.g., choice yes, choice no, choice maybe. They correctly configured a value converter to store these as strings, yes, no, maybe, in the database. Later, a new option, choice skip, was added to the enum, but the existing data in the database still contained no response values from older surveys. When they deployed the update, fetching old survey results caused an invalid cast exception because the value converter tried to convert no response from the database to a choice enum member and found no match. The fix involved modifying the value converter to include a mapping for no response to some default or choice skip enum member, or handle it gracefully as null if the column was nullable. This showed the importance of planning for data evolution and historical data when using value converters. Chapter 5. Concurrency catastrophes, handling simultaneous data changes. In any multi-user application, it's inevitable that multiple users or processes will attempt to read, modify, or delete the same piece of data at roughly the same time. This simultaneous access to shared resources introduces complex challenges known as concurrency issues. While a database system is designed to handle many requests concurrently, conflicts can arise, leading to undesirable outcomes like lost updates, inconsistent data, or application crashes. Your DB context, as the gateway to your database, plays a critical role in managing these interactions. Misunderstanding how EF Core handles concurrency or failing to implement proper strategies can transform a seemingly robust application into one riddled with subtle, hard-to-diagnose data integrity problems. This chapter delves into the complexities of concurrent data access, focusing on how EF Core helps you detect and resolve conflicts and the broader implications of transaction isolation levels. 5.1 Data Clashes: The Peril of Concurrent Modifications. Before diving into EF Core's specific mechanisms, it's important to grasp the fundamental types of concurrency problems that can arise in any database system. While several exist, the most common and impactful for application developers are the lost update. This is perhaps the most dangerous and insidious. It occurs when two or more transactions select the same row, then each updates the row based on the value it originally selected. Since each update is based on the initial, old value of the row, the second update overwrites the first, causing data to be lost without any error message. Dirty reads. One transaction reads data that has been modified by another transaction, but has not yet been committed. If the second transaction then rolls back, the first transaction has read dirty or incorrect data. Non-repeatable reads. A transaction reads a row, and then, attempting to read the same row again later within the same transaction, finds that the data has been modified by another committed transaction. The original read is no longer valid. Phantom reads. A transaction reads a set of rows satisfying a certain condition. Later, within the same transaction, it re-executes the query and finds new rows that satisfy the condition, which were inserted by another committed transaction. While database systems offer different isolation levels to mitigate these, which we'll discuss later, the lost update is particularly problematic because it often leaves no trace, delivering a quiet yet devastating blow to data integrity. EF Core, by default, provides an elegant mechanism to prevent lost updates known as optimistic concurrency. 5.2 The lost update: When optimistic concurrency is absent or misunderstood. The lost update is a common and often undetected data integrity failure. It happens when two different users or processes attempt to make changes to the same record in the database, and the later change unknowingly overwrites the earlier one. What it is? Optimistic concurrency is a strategy used to prevent lost updates without requiring database locks that could slow down your application. The optimistic part refers to the assumption that conflicts will be rare. Instead of locking records, it tracks whether a record has changed between the time it was read and the time it's written back to the database. If it has changed, a conflict is detected and your application code is notified so it can handle the situation gracefully. For EF Core to implement optimistic concurrency, you typically add a special property to your entity, known as a concurrency token. This is often a row version, a timestamp managed automatically by the database, specific to SQL Server, or a simple byte array or date-time property that you mark as a concurrency token. Why it's a problem? If you don't implement optimistic concurrency for entities that can be modified by multiple users, a lost update will simply occur. Your application will not receive an error, and the user who saved first will have their changes silently overwritten by the user who saved second. This leads to inconsistent data and frustrated users who see their work disappear. Example scenario: imagine two users, Alice and Bob, both open the sales order screen for sales order 12,345. This order has a property for discount percentage. Alice reads sales order 12,345. Discount percentage is 10%. Bob reads sales order 12,345. Discount percentage is 10%. Alice changes discount percentage to 15% and calls save changes on her DB context. The database updates successfully. Bob changes discount percentage to 12% and calls save changes on his DB context. Without optimistic concurrency, Bob's change would simply overwrite Alice's. The discount percentage would become 12%, and Alice's update to 15% would be silently lost. How to identify inconsistent data. Users report seemingly random data inconsistencies. A value might appear one way, but then change unexpectedly without any corresponding user action, or changes they know they made are no longer present. No error messages. The most problematic aspect is the absence of error messages. The application saves seem successful, but the data is simply wrong. Audit trails. Reviewing detailed audit logs might show two sequential update events for the same record with conflicting values, but no indication of an actual collision. How to fix. The most common approach involves adding a concurrency token to your entities. Row version for byte. In your C# entity, simply define a byte property named row version and mark it using the timestamp, data annotation, or isRow version in Fluent API. The database will manage this property automatically, updating it with a new value every time the row changes. EF Core will include this row version in the where clause of its update and delete statements. If its value doesn't match the database's version, it means another user modified the row, and EF Core will throw a DB update concurrency exception. Generic concurrency token for int, date, time, GUID. You can use any data type property as a concurrency token, marking it with concurrency check or isConcurrency token in Fluent API. For example, a last modified datetime property. When saving changes, your application logic would increment or update this property. EF Core includes this property in the where clause. If its value in the database doesn't match the original value read by your DB context, a DB update concurrency exception is thrown. This requires your application to manage the token's value upon update. Preventative measures. Implement for all modifiable entities. Generally, any entity that can be modified by multiple concurrent operations should have a concurrency token. Erring on the side of caution is better. Understand row version versus concurrency token. Know the difference. Row version is database generated and specific to byte arrays, offering a simpler form of optimistic concurrency. A generic concurrency token requires your application to manage its value on update. Anecdote case study. In a customer relationship management (CRM) system, sales representatives frequently updated client contact information. Alice might be updating a client's phone number, while Bob is simultaneously updating their email address. Without optimistic concurrency, if Alice saved first, Bob's later save would overwrite Alice's phone number change. The company initially saw this manifest as sales reps complaining that information they knew they entered had disappeared. By introducing a row version column on the client entity and configuring it in EF Core, the system began throwing DB update concurrency exception errors instead of silently losing data. This allowed the application to inform Alice or Bob that a conflict had occurred and provided options for resolution. 5.3 Dealing with concurrency conflicts. DB update concurrency exception. While implementing optimistic concurrency is crucial, it's only half the battle. Once EF Core detects a conflict and throws a DB update concurrency exception, your application must be prepared to handle it gracefully. Simply letting the exception crash the application is not an option. What it is? DB update concurrency exception is the specific exception type thrown by EF Core when an optimistic concurrency conflict is detected during save changes. It signifies that the entity you tried to save has been modified by another process since it was last retrieved by your current DB context. Why it's a problem? An uncaught DB update concurrency exception will cause your application to crash or return a generic error to the user, leading to a poor user experience and potentially unrecoverable data modifications. A well-designed application needs a strategy to resolve these conflicts, which can range from simply discarding one user's changes to allowing users to explicitly merge conflicting updates. Example scenario. Continuing from our previous example, Alice reads sales order 12,345. Discount percentage is 10%, row version is X. Bob reads sales order 12,345. Discount percentage is 10%. Row version is X. Alice changes discount percentage to 15% and saves. The row version in the database updates from X to Y. Bob changes discount percentage to 12% and calls save changes on his DB context. When EF core generates the update statement, its where clause includes row version equals X. The database finds no row where the row version is still X, because it's now Y, so no rows are updated. EF core detects this 0 rows affected and throws a DB update concurrency exception. Your application's code usually needs to wrap the save changes. Call in a try-catch block to intercept this exception. How to identify exception logs. The presence of DB update concurrency exception in your application's error logs is the primary indicator. User reports. Users frequently report getting an error occurred or data save failed messages, which when cross-referenced with logs reveal these exceptions. How to fix. Handling DB update concurrency exception involves several steps within your catch block. Retrieve current values. The DB update concurrency exception object provides access to 3 sets of values for the conflicting entity. Entry entity, the values currently in your application's memory, what the user tried to save. Entry original values, the values that were read from the database when the entity was first loaded into the DB context. Entry current values, the values that are currently in the database, what another user successfully saved. You typically use entry reload or entry get database values to fetch these. Choose a resolution strategy. This is a business decision based on your application's requirements. Client wins, last in wins. You disregard the changes made by the other user and force your user's changes to be saved. This updates entry original values with entry current values and retries save changes. This effectively overwrites the other user's work, which is generally undesirable unless your application specifically dictates last user to save always wins. Database wins, reload and override. You discard your user's changes and reload the latest version of the entity from the database. This effectively informs the user that their changes could not be saved because someone else updated the record, and they now see the latest version. This is safer but can frustrate users who lose work. Implemented by calling entry reload. Merge conflicts. This is often the most user-friendly approach but requires more complex UI. You or your application logic compare entry entity, your user's changes, entry original values, what you started with, and entry current values, what's now in the database. You then present the conflict to the user, e.g., in a special UI, and allow them to decide which value to keep for each conflicting property. Once resolved, you manually update the entry entity and entry original values accordingly and retry save changes. Retry logic. After applying a resolution, especially client wins or merge conflicts, you must call save changes, again within your try block or a loop. It's common to put the entire save changes operation inside a do-while loop that attempts a set number of retries. Preventative measures, consistent error handling. Implement a consistent error handling mechanism for all save changes. Calls that expect optimistic concurrency conflicts. Clear user feedback. When a conflict occurs, provide clear and actionable feedback to the user. Explain what happened and how they can resolve it. A generic error saving message is insufficient. Anecdote continuation. Using the CRM example, after implementing row version, if Bob clicked save after Alice, he would now get a DB update concurrency exception. The application's error handling for this specific exception would then reload the client entity from the database. Compare Alice's current values, the database wins values, with Bob's attempted changes, the client wins values. Display a modal dialog to Bob, showing him that Alice updated the phone number and he updated the email, asking him to decide if he wanted to keep both or prioritize one over the other. This allowed for intelligent merging, preventing data loss for either user. 5.4 Transaction isolation levels, understanding the trade-offs. Beyond preventing lost updates with optimistic concurrency, managing broader data consistency in a concurrent environment involves understanding transaction isolation levels. These settings dictate how one transaction, a series of database operations treated as a single, atomic unit, can affect or be affected by other concurrent transactions. What it is. Transaction isolation levels define the degree to which one transaction is isolated from the effects of other concurrent transactions. The ANSI ISO SQL standard defines 4 main isolation levels in ascending order of isolation, and typically, decreasing concurrency performance. Read uncommitted, lowest isolation. Transactions can read uncommitted changes made by other transactions, dirty reads. This offers the highest concurrency but the weakest data integrity. Generally, avoid unless specific, high-performance, low-integrity needs. Read committed default for most DBS and EF core. Transactions can only read changes that have been committed by other transactions, prevents dirty reads. However, it allows non-repeatable reads and phantom reads. Repeatable read prevents dirty reads and non-repeatable reads. Once a row is read, other transactions cannot modify it until the reading transaction commits. However, it still allows phantom reads. New rows inserted by another transaction might appear in subsequent reads. Serializable, highest isolation, prevents dirty reads, non-repeatable reads, and phantom reads. It's the most isolated, but often comes with the highest overhead due to extensive locking, potentially limiting concurrency. EF core, by default, typically relies on the database's default isolation level, which is commonly read committed. Why it's a problem? Incorrect data. Choosing an isolation level that is too low for your application's needs can lead to reading inconsistent or dirty data, causing logical errors in reports or application logic. Performance bottlenecks. Choosing an isolation level that is too high, e.g., serializable when not strictly necessary, can introduce excessive locking, drastically reducing concurrency, and leading to deadlocks or long waits for database operations, effectively crippling your application's scalability. Subtle bugging. Concurrency bugs can be extremely difficult to reproduce and debug because they depend on precise timing, which is hard to control in a development environment. Example scenario. Consider a complex financial reporting system that needs to generate snapshots of account balances. If you generate the report under read uncommitted, you might include transactions that are later rolled back, leading to an inaccurate report. If you generate it under read committed, you might read an account balance, then a new transaction commits for that account, and if you reread the balance, it changes non-repeatable read, leading to an inconsistent report summary. If you need to guarantee that a series of reads will return the exact same data every time within a transaction, repeatable read or serializable might be necessary, but these levels introduce more locking. How to identify. Debugging data inconsistencies. If reports based on simultaneous data show discrepancies or unexpected results that cannot be explained by race conditions in application logic, consider transaction isolation. Database profiling. High contention, many blocked queries, or frequent deadlocks in your database profiler could indicate that an overly aggressive isolation level is being used, or that basic read committed isn't sufficient for complex read patterns within a transaction. How to fix. You can explicitly set the transaction isolation level when you begin a transaction using context database begin transaction. Using begin transaction, you can specify the desired isolation level as an argument. For instance, to ensure a set of operations are isolated as serializable. Using var transaction equals context database begin transaction, isolation level serializable. /perform database operations, here /transaction.commit. Transaction scope. For scenarios where transactions might span multiple DB context instances or other Ado.NET connections, requiring a distributed transaction coordinator like MSDTC, system transactions, transaction scope can be used. You set the isolation level on the transaction scope constructor. Preventative measures. Default read committed as starting point. For most standard application operations, the default read committed isolation level provided by EF core and your database is sufficient. Analyze business needs. Only increase the isolation level when your business requirements strictly demand higher consistency, e.g., for audit-critical reports, complex multi-step financial operations. Understand the specific types of anomalies, dirty reads, non-repeatable reads, phantom reads, you are trying to prevent. Test performance. Always test the performance impact of higher isolation levels in environments that simulate production load, as they often introduce significant performance penalties due to increased locking. Anecdote: a startup offering an online ticket booking system faced a vexing bug. Occasionally, their available seats counter would be slightly off, or two users would seemingly book the same seat, even though their code had checks for seat availability. The issue stemmed from using the default read committed isolation level. During peak booking times, a user might query for available seats, transaction A. Another user might concurrently book a previously available seat, transaction B commits, and then transaction A would attempt to book that same seat, believing it was still free. While read committed prevented reading, dirty, uncommitted data, it did not prevent the non-repeatable read, where the list of available seats changed between query time and booking time. The solution involved elevating the isolation level to repeatable read or serializable for the booking process, ensuring the entire check availability and book sequence operated on an unchanging view of the database. This significantly reduced false positives and double bookings, cementing the integrity of their booking system. 5.5 When save changes fails. Graceful error handling. While EF Core can often abstract away raw SQL, it cannot abstract away the fundamental realities of database interactions. Network issues, database server errors, and semantic violations, like trying to insert duplicate primary keys or violating custom constraints, can all cause save changes to fail. A robust application must gracefully handle these failures. What it is: save changes attempts to persist all changes tracked by the DB context to the underlying database. This operation is not guaranteed to succeed and can throw various exceptions. The most common is DB update exception, which acts as a wrapper around more specific database errors. Why it's a problem: an unhandled exception during save changes will crash your application, potentially leaving the user baffled and the database in an inconsistent state. If some changes committed before the error and others didn't, which is rare for a single save changes call if done within a transaction, but possible. It's crucial to distinguish between various types of errors to provide appropriate feedback to the user or trigger specific recovery actions. Example scenario: your application tries to create a new user account, but another user or process has already created a user with the same unique username. Save changes will fail due to a unique constraint violation. The database server goes offline momentarily due to network issues or a restart. Any save changes call will fail. You attempt to save an entity with a foreign key referencing a non-existent record. How to identify application crashes, the most obvious sign. Error logs, messages like DB update exception, SQL exception, NPGSQL exception, MySQL exception, etc. in your logs, along with details of the specific constraint violated or network error. How to fix. The standard approach is to wrap save changes, calls in try-catch blocks, and then inspect the exceptions. General DB update exception catch. Always catch DB update exception. This is the base exception for most data persistence errors. Inside the catch block, you can examine x.inner exception for more specific details. For database-specific errors, you might cast x.inner exception to SQL exception. For SQL Server, NPGSQL exception for PostgreSQL, etc. SQL exception has a number property for SQL Server that often corresponds to specific error codes, e.g., 2627 for unique constraint violation, 547 for foreign key violation. This allows you to differentiate between different types of database errors. Concurrency exception, as detailed in section 5.3, specifically catch DB update concurrency exception, which is a subclass of DB update exception to handle optimistic concurrency conflicts. Other exceptions. Also consider catching more generic exceptions like DB update exception to cover a broader range of schema or data integrity issues, and perhaps even a general exception as a last resort for unanticipated problems, though you should strive for more specific catches. Preventative measures. Centralized error handling. Implement a centralized error handling mechanism, e.g., middleware in web applications, or a common utility method that intercepts DB update exception and gracefully translates it into user-friendly messages. User feedback. Always provide meaningful feedback to the user. Instead of an error occurred, tell them, the username you chose is already taken, please choose another. Or, there was a problem connecting to the database, please try again. Wrap in transactions, while save changes. Itself wraps all pending changes in a transaction by default for that specific context. It's often good practice to explicitly begin a transaction, context database begin transaction, when performing multiple save changes. Calls as part of a single logical unit of work, or when integrating with other side effects that need to be atomic with the database changes. This ensures atomicity, so either all changes commit or all roll back. Anecdote. A new customer registration form in a web application occasionally displayed a generic internal server error after submission. Users were unsure if their account was created or if they should retry. Digging into the logs, the development team found DB update exception, and within its inner exception, a SQL exception with error code 2627. Violation of unique key constraint. This clearly indicated that the chosen username or email was already in use. The fix involved adding a try-catch block around the save changes, call for new user registrations. If a DB update exception was caught, the code would inspect the inner SQL exception for error code 2627. If found, a specific user-friendly message, the chosen username or email is already registered. Please try a different one, was displayed. For other database errors, a more generic, but still graceful message was shown. This small addition dramatically improved the user experience and reduced support calls. Chapter 6. Data manipulation disasters. Efficient saves and updates. While retrieving data efficiently is crucial for application responsiveness, equally vital is how you manage data persistence, adding new records, modifying existing ones, and deleting obsolete information. The process of saving changes can introduce a unique set of pitfalls, often related to performance, the nuances of EF Core's change tracking, and handling entities that are disconnected from their DB context. This chapter explores common mistakes and best practices associated with data manipulation operations in EF Core. We'll delve into the performance implications of save changes, understand the delicate dance between tracked and untracked entities, and emphasize the importance of bulk operations for high-volume scenarios. 6.1 The cost of save changes. Performance implications. The save changes method is where the rubber meets the road. It's the moment all the changes tracked by your DB context are translated into SQL commands and sent to the database. While convenient, save changes can be surprisingly heavy if misused or invoked without understanding its underlying mechanics. What it is. When you call save changes, EF Core performs a multi-step process, detect changes. It scans all currently tracked entities, comparing their current property values to their original values, if any were loaded into the DB context. Generate SQL. For each detected change, add, modify, delete, it constructs the appropriate insert, update, or delete SQL statement. Command execution. It wraps all these SQL statements in a single database transaction, by default, and executes them against the database. Update state. Once successful, it updates the entity state of the tracked entities to unchanged and refreshes their original values. Why it's a problem. Batching overhead. EF Core batches multiple insert, update, or delete statements into a single round trip to the database when possible. However, if you add 10,000 entities and call save changes, after each one, you'll perform 10,000 separate database round trips, each incurring network latency and database overhead. This defeats the purpose of batching. Change detection overhead. If your DB context instance has been alive for a long time, a long-lived context, as discussed in Chapter 3, and is tracking many entities, the detect changes step before save changes can become very slow. EF Core has to iterate through all tracked entities and compare their values, which is CPU intensive. Memory consumption. Storing tracked entities and their original values consumes memory. A large number of tracked entities before save changes can lead to memory pressure. Transaction scope, while save changes, defaults to an internal transaction. If you're dealing with very large batches, keeping a transaction open for a long time can impact concurrency on the database. Example scenario: you are importing a large CSV file of 10,000 product records. Your code iterates through each line, creates a product entity, calls context add, product, and then immediately calls context save changes. This results in 10,000 separate database operations. In a complex business process, a single DB context instance is used across many UI interactions, accumulating hundreds or thousands of changes before a single save changes is called. The final save changes takes an unexpectedly long time. How to identify: database profiler, observe the number of commands being executed. If you see many single insert, update, delete statements when you expected a batch, or if a single save changes call takes a disproportionately long time, these are indicators. Application profiler. Tools like Visual Studio's diagnostic tools or .trace can show high CPU usage during the save changes call, especially during the detect changes phase. User complaints about latency. If users report that forms freeze or take a long time to save, especially after making many changes, save changes might be the bottleneck. How to fix batch changes. The most critical optimization is to add, update, delete all related entities within a single logical unit of work, and only call context save changes once at the very end. EF Core will automatically batch these into efficient database commands. For large imports, process data in chunks, e.g., 500 to 1,000 records at a time, call context save changes, then dispose of and recreate the DB context for the next chunk to manage memory and tracking overhead. Use as no tracking for read-only data. If you're reading entities but not modifying them, always use as no tracking to avoid adding them to the change tracker unnecessarily. This reduces the number of entities EF Core needs to scan during detect changes. Explicitly disable change tracking. For very high-performance write scenarios where you're sure you'll handle all entity states manually, you can temporarily disable automatic change detection. Context change tracker auto detect changes enabled equals false. Remember to re-enable it or call context.changetracker.detect changes manually when needed. Use this with extreme caution. Break down large operations. If a single business operation genuinely involves hundreds of thousands of changes, consider breaking it into smaller, manageable chunks, each with its own DB context, instance, and save changes. Preventative measures. Embrace unit of work pattern. Design your application services and repositories to treat save changes as the commit point for a complete transaction, not an operation to be called after every single change. Thorough testing with realistic data. Always perform performance testing with data volumes that simulate production environments. Chunking for mass operations. Develop a common utility for mass inserts, updates that handles chunking and DB context recreation to avoid performance issues. Anecdote case study. An online learning platform implemented a feature allowing instructors to bulk award completion status to students. The initial implementation iterated through 50,000 students, marked each as completed, and called context save changes for every student. The instructor's browser would spin for nearly 30 minutes, often timing out. A quick diagnosis showed 50,000 individual update statements being sent to the database. The fix was simple. Remove the save changes, call from inside the loop, and move it to happen once after all 50,000 students had been marked as completed. This reduced the operation to a single save changes call, which EF Core intelligently batched into a few hundred update statements. The process completed in under 10 seconds, transforming a broken feature into a seamless experience. 6.2 Tracking traps. Adding, updating, and deleting entities. EF Core's change tracker is powerful, but its implicit nature can lead to confusion when adding, updating, or deleting entities, especially when dealing with entities that are disconnected from the DB context that loads them. What it is, add, marks an entity and by cascade, newly associated entities as added. When save changes is called, an insert statement is generated. Remove marks an entity and by cascade, dependent entities if configured as deleted. When save changes is called, a delete statement is generated. Updating. For an already tracked entity, you simply modify its properties. The change tracker detects these changes, and when save changes is called, an update statement is generated for only the modified properties. Update method. Used primarily for disconnected entities, i.e., entities that were not loaded by the current DB context instance. Calling context update entity marks the entity as modified by default, and save changes will generate an update statement. This is often where problems begin. Attach method. Used to explicitly tell the DB context to begin tracking a disconnected entity without assuming it has changed. It sets the entity's state to unchanged. You would then explicitly change its state to modified if properties were changed or deleted if it's to be removed. Why it's a problem? Update on unchanged entity. If you call context update entity on a disconnected entity that you think might have changed but actually hasn't, EF Core will still generate an update statement for all properties, even if they haven't logically changed. This causes unnecessary database load and transaction logs. Update for partial updates. If you only change one property of a disconnected entity and call update, EF Core will often mark all properties as modified and include them in the update statement. This is inefficient if only a few properties truly changed. Overwriting unloaded data. If your update pattern uses update on a disconnected entity, and you only supply a partial entity, e.g., only id and name, EF Core will default any omitted non-nullable properties in your entity class, if they are not explicitly set or loaded, to their default C-hash values, and those will be written to the database, potentially overwriting existing, valid data with nulls or default values. Incorrect state management. If you don't correctly manage entity state for disconnected entities, e.g., calling add on an entity that already exists in the database, you can get duplicate primary key errors or other DB update exceptions. Example scenario: Web API update. A common scenario: a front-end client posts an updated product object to your API. This product object is currently disconnected from your DB context. Bad pattern. Context.productsUpdate, product from client, context save changes. This might lead to all properties being updated or overwriting unsupplied properties. Better pattern for full update. Context entry product from client. State equals entity state modified. Context save changes. This is slightly better than update, but still updates all properties. Adding an existing entity. You attempt context add entity where entity already has a primary key that exists in the database. Save changes will fail due to a duplicate key. How to identify SQL profiling. Observe update statements. If many columns are updated when only a few logically changed, or if you see update statements for records you didn't intend to modify, your tracking logic might be flawed. DB update exception. Errors related to duplicate keys or foreign key violations often indicate incorrect add or update calls. Data corruption. Unexpected null values appearing in your database columns after an update. How to fix. Load modify save pattern preferred for updates. For updating existing entities, especially disconnected ones, the safest and most explicit pattern is load. Retrieve the entity from the database using the current DB context instance. var existing product equals context.productsFind, product from client ID. Check null. If existing product is null, the entity doesn't exist, and you should handle this, e.g., throw a not found exception. Apply changes. Manually copy the modified property values from your product from client object to the existing product, the one currently tracked by the DB context. You can use a mapping library like AutoMapper for this. Mapper map product from client, existing product. Save. Call context save changes. EF Core's change tracker will automatically detect which properties actually changed on existing product and generate an update statement for only those specific columns. This is highly efficient and safe. Batching with separate DB contexts. For mass updates of disconnected entities, it may be more efficient to create a new DB context for each batch, attach entities using attach, explicitly mark specific properties as modified, and then save changes. Example, context attach product from client, context entry product from client. Property p equals p.name is modified equals true, context save changes. This is more granular but requires more manual state management. Correct add/remove. Usage, ensure add, is only called for truly new entities. Remove should be used for entities you want to delete. Preventative measures. Standardize update logic. Encapsulate your update patterns in reusable methods or a dedicated service layer to ensure consistency and correctness across your application. Test update scenarios. Thoroughly test partial updates, full updates, and update attempts on non-existent records. Understand entity state. Grasp the concept of entity state and how methods like add, update, attach, and remove transition entities between states. Anecdote: a client reported that their product management system sometimes resets certain product attributes, like weight or dimensions, to 0 or default values after updates, even though the user didn't touch those fields in the UI. The investigation revealed that the API endpoint for product updates simply copied the submitted DTO directly to the database using context.productsUpdate, product DTO. The DTO coming from the client only contained the fields relevant to the UI form, often omitting fields that were not editable or simply not present on that particular form. Since the DTO's weight property might be 0, the default for double, and the dimensions object might be null, EF-Core's update method, when applied to a disconnected object, would mark those properties as modified and update them in the database, inadvertently overwriting the real, valid data with zeros or nulls. Switching to the load-modify-save pattern, where only specific properties from the DTO were mapped to a newly loaded tracked entity, immediately resolved the data corruption, ensuring only intended changes were persisted. 6.3 Disconnected entities. Bridging the gap between UI and database. The disconnected entity scenario is extremely common, especially in web applications where data is sent to a client, e.g., browser, mobile app, potentially modified, and then sent back to the server for persistence. Successfully handling these entities is critical. What it is? A disconnected entity is a C-hash object representing a database record that was either created in your application code without being loaded from the database by a DB context, loaded by one DB context instance, serialized, e.g., to JSON, sent to a client, deserialized back into a C-hash object, and then passed to another, new DB context instance for an update or deletion. Crucially, a disconnected entity is not tracked by the DB context instance you are currently trying to use for persistence. Why it's a problem? Change tracker ignorance. Since the DB context is unaware of the entity's history or its original values, it doesn't know which properties have changed. It needs explicit instructions. Potential for inefficient updates. As discussed in 6.2, naive use of update can lead to all properties being updated or data loss. Concurrency conflicts. Without tracking original values, EF-Core cannot perform optimistic concurrency checks automatically for disconnected entities. You must manage this manually. Relationship management. Handling relationships on disconnected entities can be tricky. If a disconnected parent entity has a list of disconnected child entities, e.g., an order with order items, correctly informing EF-Core about the state of each child, added, modified, deleted, is complex. Example scenario: typical web post PUT. A front-end form sends a JSON payload representing a customer with updated name and email. Your controller receives this customer object. This is a disconnected customer. Background processing. A background service processes a message queue where messages contain order objects to be updated. These order objects are deserialized from the message and are disconnected. How to identify? No errors, but no updates. You call save changes. No error occurs, but no update statement is generated because the DB context doesn't know the entity needs updating. DB update exception related to state. Errors stating an entity cannot be tracked because it has an existing identity, already added, or other state-related exceptions. Missing concurrency checks. If optimistic concurrency is configured but DB update concurrency exception isn't thrown when conflicts occur for disconnected updates, it's because EF core isn't correctly tracking the original state. How to fix: load modify save, best practice for single entity updates. As detailed in section 6.2, load the existing entity, apply changes from the disconnected entity, and save. This approach simplifies concurrency checks if the loaded entity has a concurrency token. Attach and manual state management for fine-grained control. Context attach disconnected entity, set state to unchanged. Context entry disconnected entity. Property p equals p dot property name is modified equals true. Explicitly mark only changed properties. Context save changes. This approach is efficient for partial updates, but is more verbose and error-prone if you forget to mark properties. Handling related entities on disconnected graphs. This is complex. For a parent with children, e.g., order with order items, load existing graph. Load the entire existing order and its order items from the database first. Compare and merge. Iterate through the disconnected order items. For each item, if it has an ID, check if it exists in the existing order items. If so, update the existing one. If it's new, no ID or ID is default for new, context add, new item. Identify removed items. Find items in the existing order items that are not present in the disconnected order items and context remove item. This manual diffing can be substantial. For complex, nested graphs, this becomes a significant effort. AutoMapper extensions for complex graphs. Libraries like AutoMapper have extensions for EF core, AutoMapper EF6 extended, or custom solutions that can help automate the diffing and state management for complex disconnected graphs, greatly simplifying the code. Domain-driven design and aggregate roots. In more complex applications, designing your entities around aggregate roots. A single entity that owns and controls consistency for a cluster of related entities, loaded and saved as a single unit, can simplify persistence logic for disconnected graphs. Preventative measures. Client-side original data. For scenarios where optimistic concurrency is required for disconnected updates, consider sending the concurrency token or row version back to the client and having the client send it back with the update request. Then, when using the load modify save pattern, you can manually check the incoming concurrency token against the loaded entity's concurrency token before saving. Specific API endpoints. Create separate API endpoints for adding, full updates, and partial updates if the logic varies significantly, providing clearer contractual boundaries. Anecdote. A content management system allowed users to organize articles into complex nested categories. When a user rearranged categories, adding, removing, reordering, the entire tree was sent back to the server as a disconnected object graph. The initial server-side logic simply called context entry, disconnected category. State equals entity state modified on the root category and save changes. This correctly persisted changes to the root category itself, but completely failed to detect added, removed, or reordered children categories. The solution required a sophisticated diffing algorithm. It would load the entire existing category tree from the database, then iterate through the incoming disconnected tree, comparing each node. If a child was new, it was added. If it was present in the old tree but not the new, it was marked for removal. If it was present in both, its properties were updated. This manual delta tracking over the disconnected graph was much more complex than anticipated but essential for correct data persistence. 6.4 Bulk operations. Avoiding the row-by-row grind. While EF core is excellent for individual entity operations, its default behavior of transmitting changes one by one, even if batched, can become a significant performance bottleneck when dealing with truly large-scale data manipulation. What it is? Bulk operations refer to performing a large number of insert, update, or delete operations on a database in a single, highly efficient command, often by leveraging database-specific features or optimized libraries. EF core's default save changes, while batching still translates each entity change into a separate SQL statement sent to the database. Why it's a problem? Performance bottleneck. The primary issue is performance. While EF Core batches multiple insert statements into one network round-trip, it still generates one insert statement per entity. For update and delete, it's usually one statement per entity. If you need to insert 100,000 records, update 50,000, or delete 20,000, the cumulative overhead of parsing many individual SQL statements on the database server, even in a batch, is much higher than a single bulk command. Memory consumption and change tracking overhead. For large bulk operations, attempting to track all 100,000 entities in a DB context before calling save changes will consume massive amounts of memory and CPU during the change detection phase. Scalability limitations. Features that rely on large-scale data modifications, e.g., data migrations, nightly ETL processes, reporting calculations, can become unusable due to the row-by-row grind of standard EF Core operations. Example scenario: user data migration. You need to migrate millions of user records from an old system to a new one. Iterating and context add, user, context save changes, in chunks might still take hours. Price updates. All products in a specific category need their prices increased by 10%. Doing this row by row would be highly inefficient. Archiving old data, deleting all records older than a certain date for compliance reasons. How to identify very long-running queries operations. Operations that involve thousands or millions of records take an unacceptably long time. High CPU on database server. When running large operations, the database server shows high CPU usage consistently, indicating it's processing many individual statements. High network bandwidth traffic. Large amounts of data being sent back and forth between application and database for operations that should be simple. How to fix EF Core extensions for bulk operations. Several third-party libraries provide highly optimized bulk operations for EF Core, often leveraging underlying ado.NET SQL bulk copy for SQL Server or similar database-specific features. Popular options include EF Core bulk extensions, offers bulk insert, bulk update, bulk delete, and bulk merge. These can drastically improve performance for mass operations by sending data in large chunks directly to the database or generating single, set-based update-delete queries. Z-Entity Framework plus EF Core, another comprehensive suite with similar bulk features. Raw SQL commands. For simple, set-based updates or deletes, you can execute raw SQL directly. This bypasses EF Core's change tracking completely, but gives you maximum control and performance. Example for bulk update. Context database execute SQL raw. Update products set price equals price 1.10 where categoryid equals 0, categoryid. Example for bulk delete. Context database execute SQL raw. Delete from old logs where log date 0, date time UTC now add years -1, stored procedures. For highly complex bulk operations or critical performance paths, encapsulating the logic in a stored procedure and calling it from EF Core can be the most performant option. Preventative measures. Proactively identify bulk needs. During an application's design phase, identify scenarios that will predictably involve large data sets and plan for bulk operations. Don't over-optimize smaller operations. For operations involving dozens or hundreds of records, save changes with proper batching is usually perfectly adequate. Only introduce bulk libraries or raw SQL for operations where performance is critical and row-by-row save changes is a known bottleneck. Understand implications. Bulk operations bypass EF Core's change tracking completely, which means entities involved in bulk operations are not tracked by your DB context. If you need those entities to be part of the DB context's in-memory graph after the operation, you'll need to reload them. Anecdote. A large healthcare provider used a system that generated nightly reports. Part of this process involved calculating a vast number of health metrics for millions of patient records and saving results, metric result entities. The initial design used EF Core's context add, result, in a loop chunking save changes, every 10,000 records, While better than saving one by one, the entire process still took over 8 hours, causing reports to be late. By incorporating EF Core Bulk Extension's bulk insert method, the process of writing millions of metric result entities to the database was reduced from multiple hours to just under 15 minutes. This dramatic improvement allowed the reports to be generated on time, freeing up valuable compute resources and making the overnight processing window feasible. It was a clear demonstration of how choosing the right tool for mass data manipulation can lead to order-of-magnitude performance gains. Chapter 7: Migration Mishaps. Evolving your database safely. Database schema evolution is an inescapable part of software development. As applications grow and business requirements change, your data model must adapt, meaning tables need new columns, relationships shift, and data types may be altered. Entity Framework Core's Migrations feature is designed precisely for this. To manage the delicate process of evolving your database schema to match your application's DB context model, all while preserving existing data. However, the power and convenience of EF Core migrations can mask significant pitfalls. Mismanagement of migrations can lead to accidental data loss, schema inconsistencies, deployment failures, and a tangled version history that is difficult to untangle. This chapter explores common migration mishaps, from the dangers of manual intervention to managing complex migration histories and safely deploying schema changes. 7.1 Manual Migration Edits. The road to ruin. EF Core migrations are primarily code first. You make changes to your CHDB context and entity classes, and then EF Core generates code files that represent the schema changes needed to update your database. While these generated files are C# code and theoretically editable, manually altering them is a strong anti-pattern that often leads to major problems. What it is. This pitfall occurs when developers directly modify the C# code within the migration files, e.g., the up and down methods generated by the add migration command, rather than letting EF Core manage the diffing process. This might be done to add custom SQL, rename columns without data loss, or fix perceived issues. Why it's a problem? Loss of implied state. The migration files generated by EF Core aren't just a list of SQL commands. They represent a snapshot of your DB context model at the time the migration was created. EF Core uses this internal model snapshot, stored in a companion designer.cs file for each migration, to calculate the next migration. If you manually change the SQL executed by the up method without updating the internal model snapshot, EF Core's understanding of your database schema, derived from DB context, and the actual database schema, after running your modified migration, will diverge. Next migration may be incorrect. Because of this divergence, the next time you try to add migration, EF Core compares your current DB context model against the misaligned internal saved model from your manually edited migration. It might think changes were made that weren't, or miss changes that were made, generating an inaccurate up and down for the new migration. This leads to broken migration chains. Rollback problems down method. If you alter an up method, you are then solely responsible for ensuring the corresponding down method correctly reverses those changes. Manual edits complicate this, making rollbacks unreliable. Team collaboration issues. When multiple developers are working on a project, manual migration edits can cause conflicts and confusion. One developer might have a locally modified migration that clashes with what's in source control, leading to update database failures or merge conflicts. Data loss potential. If you insert custom SQL to rename a column in up, but forget to handle the data transfer properly, or if your down method doesn't correctly revert the change, you can lose data. Example scenario. A developer needs to rename a column product.description to product.long.description. Instead of adding a new migration that renames the column, which EF Core can do, they manually edit the previous migration, perhaps the initial creation migration, changing the create table in up from description to long description, skipping the EF Core diffing process. How to identify unexpected, empty migrations. You make significant changes to your entity model and then run add migration, but EF Core generates an empty migration file no operations in up or down. This is a big red flag indicating that EF Core's internal model snapshot is out of sync. Inconsistent schema. The schema created by applying migrations locally doesn't match what the DB context model describes, leading to runtime errors. Merge conflicts in migration files. Frequent and perplexing merge conflicts in migration C-hash files, especially in the Designer CS companion files. Update database errors after pulling changes. Your local database might be fine, but after pulling changes from source control, update database fails or produces unexpected schema changes on your local instance. How to fix? Let EF Core generate diff first. Always let add migration generate the C-hash migration files based on the difference between your current DB context model and the most recent model snapshot. Apply custom operations after generation. If you need to perform actions that EF Core doesn't directly support, e.g., renaming a column and preserving data, adding a non-nullable column to an existing table without a default and populating it, you should add these operations after add migration has generated the diff. Open the generated migration file and insert your custom SQL. Commands between the generated operations or use rename column, add column, with default value SQL, etc. within the generated up and down methods. Correcting mistakes. If you've already manually edited a migration, the cleanest way to fix it is often to revert that migration, remove migration, undo your manual C-hash changes, fix your DB context model, and then regenerate a clean migration. For migrations that were already applied to shared environments, e.g., test or production, this approach becomes problematic. In such cases, a more advanced strategy might be needed, such as creating a fix-up migration that corrects the schema divergence. Preventative measures. Review generated migrations. Always open and review the contents of a newly generated migration file before committing it. Ensure it accurately reflects your intended changes. Trust EF Core's diffing. Allow EF Core to do its job. It's smart enough to figure out renaming if you use the column, old name, data annotation, or Fluent APIs has column name, old name, before generating the migration that renames it. Automate migration application. Use tools or scripts to apply migrations to target environments to ensure consistency across deployments. Anecdote case study. A team was working on a project with a rapidly evolving database schema. One developer needed to add a new column to an existing table users. Instead of creating a new migration, they manually added the column to the up method of the initial creation migration, bypassing the EF Core diffing process. This worked fine on their local machine. However, when the time came to deploy, update database failed on the CI server. The server's database had already been updated to the initial creation migration, but without the new column present. When EF Core compared its model snapshot, which still reflected the original initial creation migration, to the modified one, it saw no difference, leading to an empty add migration when a new database change was added. Fixing this required recreating the database locally, running all migrations to truly see the difference, and then creating a fix-up migration that re-added the supposedly new column, which was already present in the manually edited migration, to bring the migration history back in sync. This incident highlighted how manual editing could corrupt the very history that migrations are designed to manage. 7.2 Migration Data Loss, the unforgivable sin. The primary goal of database schema evolution is to update the structure while preserving existing data. Accidental data loss during a migration is perhaps the most catastrophic mishap, resulting in irreversible damage and significant operational headaches. What it is. This pitfall occurs when migration operations inadvertently delete or corrupt existing data. Common causes include dropping a column, removing a property from a C-hash entity without understanding that it will translate to a drop column SQL statement, which permanently deletes all data in that column, changing a data type, altering a C-hash property's data type, e.g., string to int, where the existing data cannot be automatically or safely converted by the database. Non-nullable column addition. Adding a new non-nullable column to an existing table without providing a default value or handling the existing null data, causing insertion errors or forced default values for existing rows. Renaming tables columns. If not handled carefully, renaming can be interpreted as a drop followed by a create, leading to data loss. Why it's a problem? Data loss is severe. Depending on the data lost, it can lead to operational stoppage. If critical data is lost, the application may become unusable. Reputation damage. Loss of customer data is a major breach of trust. Legal compliance issues. Depending on the industry, loss of certain data can have legal repercussions. Difficult recovery. Recovering lost data often involves cumbersome, time-consuming processes like restoring from backups, which may not be up to date, or manually re-entering data. Example scenario. A developer deletes a notes property from a customer entity in C# because they think it's no longer used. When a migration is generated and applied, the notes column, and all its valuable customer information, is dropped from the customer's table. A C# string property storing user IDs, e.g., U001, U002, is changed to an int property. When migration runs, existing string values cannot be converted to integers, potentially causing data truncation or errors. How to identify? Review generated migration SQL. Always examine the raw SQL produced by add migration for drop table, drop column, or alter column statements that you didn't explicitly intend to cause data destruction. This is your primary safeguard. Test on realistic data. Apply your migrations to a copy of your production database or a database populated with realistic dummy data to catch data loss scenarios before they reach production. Backup strategy. While not identification, having solid database backups is the ultimate safety net. How to fix? Intentional column drop. If you intend to drop a column but need to preserve its data first, e.g., migrate it to another table, you must carry out the migration in multiple steps. First, create a new column, copy data programmatically, then drop the old column in a subsequent migration after verifying data integrity. Safe renaming. For renaming columns, tables in EF Core, use rename column or rename table inside your up and down methods in the migration C# file. This tells EF Core to generate a sprename SQL Server or equivalent command, preserving data. Handling non-nullable column additions. When adding a new non-nullable column, you must provide a default value or default value SQL in your migration. This ensures existing rows get a non-null value. For example, migration builder add column bool is active, products default value true, type conversion strategy. For data type changes where conversion is lossy or complex, consider a multi-step approach. Add a new column with the new data type. Migrate data from the old column to the new column programmatically, e.g., using SQL, commands in the migration, or a separate script. Remove the old column in a subsequent migration. Update your application model to use the new column. Preventative measures. Migrations are code. Treat migration files as critical C# code. Review them thoroughly, use source control, and demand high quality. No auto-deletion. Never use database ensure deleted, followed by database ensure created in production code. Use migrate instead. Automated backups. Implement a robust database backup and restore strategy. You need a safety net when dealing with schema changes. Anecdote case study. A critical e-commerce platform experienced a catastrophic data loss event. In a rush, a developer cleaned up the database model by removing a few supposedly unused properties from some C# entities like order attributes and customer preferences. On deployment, update database ran smoothly. However, the next morning, support calls flooded in. Customers couldn't load their past order details, and their saved preferences were gone. The removed C# properties translated directly to drop column commands, which silently deleted years of valuable historical data that was not actively used by the new application, but was still vital for historical reporting and compliance. This irreversible error caused significant downtime, required a costly restore from a slightly outdated backup, and led to a mandatory company-wide policy of peer-reviewing all generated migration SQL before deployment to any shared environment. 7.3. Managing divergent migration histories in teams. In a team environment, managing migrations across multiple developers and feature branches can quickly become a tangled mess. Divergent migration histories arise when different developers introduce changes to the database schema in parallel. What it is? This pitfall surfaces when developers create migrations independently on different branches. Migrations are reordered or deleted in source control. Developers forget to update database locally after pulling new migrations, leading to their local database schema being out of sync with the true head of the migration chain. Different environments, e.g., QA, staging, production, have different applied migration states. Why it's a problem? Update database failures. When merging branches, an update database on a developer's local machine might fail because the ordering of migrations is incorrect, or a migration might try to apply an operation that was already applied by another migration in a different order. Merge conflicts. Frequent and tricky merge conflicts in the migration C hash files, especially the highly sensitive designer CS snapshots. Inconsistent environments. Different deployed environments might end up with slightly different schema versions, making debugging and testing deployment very difficult. Developer friction. Time wasted by developers resolving migration conflicts or recreating local databases. Example scenario. Developer A creates migration A on branch A. Developer B creates migration B on branch B. Based on the same common ancestor, as branch A, both branches are merged into main. The order of migration A and migration B in main might be arbitrary, leading to update database issues for developers whose local databases might have one applied before the other, or for CI/CD pipelines. How to identify local update database failures. Your local update database command consistently fails after pulling main. Git merge conflicts. Numerous merge conflicts in the migrations folder, specifically in the auto-generated files. Schema compare tools. Using a schema comparison tool between databases from different environments shows unexpected differences, even if all migrations were supposedly applied. How to fix. Pull before migrating. As a strict team policy, always pull the latest changes from main or your integration branch before creating a new migration. This ensures your new migration is based on the latest schema. Branch-specific migrations. Careful merging. When merging feature branches, ensure that the order of migrations in the target branch's migrations folder is correct. Git will usually merge them by commit date, but manual intervention might be needed if multiple migrations are created concurrently. Shared migration baseline. For very large teams or long-lived branches, consider a policy where a baseline migration is created periodically, squashing all previous migrations into one. This helps reduce the number of potential conflicts, but requires careful coordination. Recreating local database as last resort. If a developer's local migration history becomes irreparably tangled, the quick, though frustrating, fix is often to delete the local database, .NET F database update from scratch, and reseed with test data. This should not be a frequent occurrence. Use .NET F migrations script. For deployment, generate a single SQL script to apply all outstanding migrations using .NET F migrations script output script SQL idempotent. This script can then be applied to environments, ensuring consistency. Preventative measures. Source control etiquette. Educate the team on proper source control workflow, especially around merging and rebase strategies for branches containing migrations. Dedicated migration review. Include migration files in code reviews. Ensure generated SQL makes sense and that no manual edits or accidental reordering occurred. CI/CD pipeline. Implement CI/CD to automatically apply migrations to test databases or generate deployment scripts, catching issues early. Anecdote case study. A large development team adopted feature branching heavily. Each team would work on their features, adding migrations, and then merge back to develop. A persistent problem was that when a developer pulled develop and ran update database, it would randomly fail, or worse, apparently succeed, but leave their local database in a corrupted state, where tables or columns were unexpectedly missing or had incorrect types. The root cause was git merge often reordering the C hash migration files from different branches arbitrarily. When update database ran, it would apply them in the wrong sequence, leading to errors. The solution adopted involved a policy. Always get pull rebase develop immediately before creating a new migration, and a stricter code review process for migration files. For extreme cases, they adopted a quarterly squash migration, where all past migrations were consolidated into a single baseline, simplifying future merges. 7.4 Seed data strategies. Populate safely. Often, a database needs initial data for the application to function, e.g., administrative users, default settings, lookup tables that rarely change. This seed data needs to be managed alongside schema changes. Incorrect seeding can lead to duplicate records, lost changes, or inefficient deployments. What it is. Seed data is static or commonly required data that is inserted into your database as part of the migration process. EF Core allows you to do this in the onModel creating method using hasData. Why it's a problem. Duplicate data. If hasData is used carelessly, it can attempt to reinsert data on every update database, leading to duplicate primary key errors or duplicate rows if not handled correctly. Lost manual changes. If hasData is used for data that might be modified by users, e.g., default categories, subsequent update database calls might overwrite those manual changes. Inefficient for large datasets. hasData typically generates insert statements directly in the migration. For very large seed datasets, this can bloat migration files and slow down updates. Maintaining state. When an entity being seeded has external dependencies, e.g., foreign keys, ensuring correct ID values are used is crucial. Example scenario. You initially seed default product category data using hasData. Later, a user modifies the name of one of these categories via the UI. When update database runs again, it might try to reseed the original name, potentially reverting the user's change or causing a conflict. You seed 10,000 lookup entries, making your migration file massive and update database very slow. How to identify duplicate key errors on seeded entities. After running update database, you get errors about duplicate primary keys for your seeded entities. User-reported data reversions. Users report that their changes to seemingly static data, e.g., default settings, are being reverted after deployments. Bloated migration files. Migration files become unusually large due to many hasData calls. How to fix hasData for immutable lookup data. hasData is best suited for truly static lookup data that is unlikely to change or will never be modified directly by users, e.g., active, inactive statuses, currency codes, application constants. For subsequent migrations, hasData will perform an insert if the record doesn't exist and an update if it does, based on the primary key. This generally works for updating existing seed data. Separate seeding logic. For dynamic seed data or data that might be user-modified, do not use hasData. Instead, use a programmatic seeding approach. Create a separate method, e.g., mydb context seed data, that you call explicitly after migration builder migrate. Within this method, check for the existence of records before updating them, e.g., context roles any. Use context add for new records and then context save changes. This allows you to manage the seeding process more precisely, preventing duplicates and unintentional overwrites. SQL script for large seeds. For very large seed datasets, consider managing the data in separate SQL scripts, e.g., SQL files that you execute manually after migrations, or as part of your deployment pipeline, bypassing hasData entirely. Preventative measures. Categorize data. Classify your static data. Is it immutable, never changes, perfect for hasData, or might it be user-modified, requires programmatic check before update? Idempotent seeding. Ensure your seeding logic is idempotent, meaning you can run it multiple times without causing duplicates or errors. This usually involves checking for existing records before adding or updating. Separation of concerns. Keep schema definitions and initial data population a clear concern, but don't mix up long-running data maintenance with schema migrations. Anecdote case study. An internal tool used EF Core migrations for everything, including seeding default user roles. Initially, they used hasData for admin, user, and guest roles. Later, new roles were added, and existing ones were sometimes renamed for clarity. Every time update database was run, the roles would either be reset to their initial names, overwriting manual changes, or developers had to delete and recreate their local databases. The issue was has data would update or insert based on primary key. If a role's name was changed in code, has data would update the existing record with the new name. If an id was changed, has data would insert a new role and not delete the old one. The fix was to switch to programmatic seeding. After context database migrate, they would call context seed roles. This method would check if each role existed by its name. If found, it would update properties cautiously. If not, it would add. This allowed for proper versioning and non-destructive updates of seed data. Chapter 8, Performance Paralysis. Advanced Optimization Techniques. Even after addressing common pitfalls like N+1 queries, client-side evaluation, and as-no tracking. As discussed in Chapter 2, your application might still suffer from performance issues. This is often because the bottlenecks are more subtle, requiring a deeper understanding of database internals and EF Core's advanced capabilities. Getting to the root of these deeper performance problems is crucial for scalable and responsive applications. This chapter delves into advanced optimization techniques that go beyond the basic querying mistakes. We'll explore the critical role of database indexing, the strategic use of raw SQL or stored procedures where EF Core falls short, and the nuances of lazy loading and compiled queries, along with their potential misuses. 8.1 Indexing and Difference, the unseen performance boost. Database indexes are arguably the single most important factor in query performance for larger datasets. However, they are frequently overlooked or misunderstood by application developers, often leading to sluggish database interactions. What it is? An index in a database is like an index in a book. Instead of scanning the entire book, table, page by page, row by row, to find specific information, an index provides a quick lookup mechanism to directly locate the relevant data. Indexes dramatically speed up data retrieval operations, select statements, but they add overhead to data modification operations, insert, update, delete, because the index itself must also be updated. Why it's a problem. Slow queries. The most immediate and obvious symptom of missing or incorrect indexes is slow query execution. For tables with hundreds of thousands or millions of rows, a simple where clause without an appropriate index can force the database to perform a full table scan, consuming massive amounts of CPU and I/O. Application lag. Slow queries directly translate to a sluggish user experience, timeouts, and increased resource consumption on both the application server and the database server. Database burden. Unoptimized queries due to missing indexes can put unnecessary strain on your database system, impacting other queries and overall database health. Example scenario. You have an orders table with a customer ID foreign key, but you frequently query for orders placed by a specific customer. Context orders where O equals O customer ID equals some ID to list. If there's no index on the customer ID column, the database will scan every order to find those for some ID. You often sort results by order date. Context orders order by descending O equals O order date to list. Without an index on order date, the database has to sort all records every time, which is very inefficient. You have a search feature on product.name using string.contains. While a full text index might be ideal here, a standard index might help for starts with or exact matches. How to identify. Database query profiling monitoring. Tools provided by your database system, e.g., SQL Server Management Studio's execution plan, PostgreSQL's explain analyze, MySQL's explain, are indispensable. They will show you which operations are causing bottlenecks, indicate when full table scans are occurring, and suggest missing indexes. This is the most crucial step. Query logs. Enable detailed query logging for EF Core to see the raw SQL being executed. Then, use that SQL in a database client to analyze its performance. Symptoms. Pages loading slowly when filtering, sorting, or searching on particular columns. How to fix. Add indexes via EF Core Fluent API. You can define indexes directly in your DB contexts on model creating method using a fluent API call. This is the preferred way as it makes your indexing part of your migration history. Single column model builder entity order has index O equals O customer id, composite index multiple columns. Model builder entity order has index O new O order date O customer id. Composite indexes are useful for queries that filter or sort on multiple columns together. Unique index. Model builder entity user has index U equals U email is unique. This enforces uniqueness at the database level. Via data annotations, you can also use index attributes directly on your entity properties available from EF Core 5.0 onwards, but Fluent API provides more control. Review query execution plans. After adding an index, rerun your explain or show the execution plan for the specific query to confirm that the database is now utilizing the index as expected. Consider included columns. For very specific query patterns, you can add include properties to an index to have additional columns stored directly within the index, avoiding a separate lookup to the main table store. This is especially useful for covering indexes, where all columns needed by the query are in the index. Full text search. For advanced text searching, like partial matches within large text fields, consider database-specific full text search capabilities and integrate them using raw SQL where needed. Preventative measures. Index foreign keys. By default, EF Core creates indexes on foreign key columns, but double-check if your most frequently used foreign keys are indexed. Index frequently queried /filtered /sorted columns. Any column used frequently in where clauses, order by clauses, or join conditions is a candidate for an index. Avoid overindexing. Adding too many indexes can negatively impact insert, update, and delete performance. Each index must be updated during data modification. Focus on the most critical queries. Regular database monitoring. Monitor your database for slow queries and periodically review suggested indexes from your database system. Anecdote case study. A company's internal bug tracking system became extremely slow as the number of tickets grew to millions. The primary bottleneck was the search issues page, which allowed filtering by status, assignee, created date, and a keyword in the title. Analysis of the database query plans revealed full table scans on the issues table whenever filters were applied. While status and assignee were foreign keys and indexed by default, created date and title, for specific keyword searches, were not adequately indexed. Adding a composite index on status, assignee, created date, and a separate index on title dramatically improved search performance. Pages that previously took 10 to 15 seconds to load now rendered in under a second. This illustrated that even with EF Core database optimization knowledge, particularly indexing, remains indispensable. 8.2 When raw SQL or stored procedures shine. Escaping the ORM wall. While EF Core is powerful at translating LINQ queries into SQL, it's not perfect. There are scenarios where generating the optimal SQL is beyond its capabilities, or where database-specific features are simply not exposed via LINQ. In these cases, opting for raw SQL or stored procedures can provide significant performance benefits and access to advanced database functionality. What it is, raw SQL, directly executing SQL queries or command strings against the database using from SQL raw, execute SQL raw, or execute SQL interpolated. Stored procedures. Precompiled SQL code stored within the database. They can complex logic, transactions, and performance optimizations specific to the database system. Why it's a problem? EF Core limitations. EF Core's LINQ translation engine cannot handle every possible SQL construct. Complex case statements, window functions, ROW and UMBR, rank, deeply nested subqueries, common table expressions, CTEs, or database-specific functions might not translate optimally or at all. This can lead to inefficient queries or force client-side evaluation. Performance for bulk operations. As discussed in Chapter 6, for large-scale insert, update, or delete operations, raw SQL leveraging specific database features, like SQL Server's bulk insert or truncate table or optimized update. where commands often vastly outperforms row-by-row operations generated by EF Core. Leveraging database features. Databases offer powerful features like full-text search, spatial data types, XML/JSON processing functions, or advanced aggregations that are not directly exposed in LINQ and need direct SQL interaction. Complex business logic. Sometimes, very complex reporting queries or data transformation logic is better encapsulated and optimized within the database as a stored procedure. Example scenario. You need a complex report calculating customer lifetime value, involving multiple subqueries, aggregations, and case statements that are difficult or impossible to express efficiently in LINQ. You need to update the salaries of 50,000 employees based on complex criteria, and context employees where E equals to list. For each E equals E salary equals 1.10, context save changes would be extremely slow. A single update statement with a where clause is far more efficient. You perform a nightly cleanup process on a log table, needing to delete millions of old records. How to identify complex LINQ generating inefficient SQL. Use a SQL profiler to see the actual SQL that EF Core generates from your LINQ queries. If it's overly verbose, contains many subqueries for simple operations, or performs multiple round trips where one should suffice, consider raw SQL. Client-side evaluation warnings. As seen in Chapter 2, if EF Core gives up translating your query, raw SQL might be the answer. Performance bottlenecks with large datasets. Operations involving large numbers of records are slow, even with proper eager loading and as-no tracking. How to fix. From SQL Raw, for read queries. For select statements, use context set T-entity. From SQL Raw, select from my table where id equals 0, some ID, to list. Be cautious with SQL injection when using from SQL Raw, always parameterize inputs. Execute SQL Raw, /execute SQL interpolated, for non-query operations. For insert update delete and other DDLDML, use context database execute SQL Raw. Update product set price equals price 1.10, where categoryid equals 0, categoryid. Execute SQL interpolated. Offers interpolated string syntax, which provides automatic parameterization and is generally safer. Context database execute SQL interpolated. Update product set price equals price 1.10, where categoryid equals categoryid. Stored procedure calls. Invoke stored procedures through from SQL Raw, for selects, if the procedure returns a result set mapping to an entity, or execute SQL Raw, for non-query procedures. View models projections. When using raw SQL for select statements that don't map to a full entity, you can map the results to a simple POCO, plain old C hash object, or a DTO. Preventative measures. Don't fear raw SQL. Recognize that raw SQL and stored procedures are valid, powerful tools. They aren't a sign of ORM failure, but rather a targeted decision for specific performance-critical or complex scenarios. Encapsulate raw SQL. Wrap raw SQL or stored procedure calls within your repository or data access layer to keep it isolated from the rest of your application code. This aids maintainability and testability. Security, always use parameterized queries, zero or interpolated strings, to prevent SQL injection attacks. Never concatenate user input directly into SQL strings. Anecdote case study. A SaaS application's most frequently accessed page was a complex analytics dashboard for business users. The data visualization required aggregating data from several large tables, performing complex calculations, and applying various filters, many of which involved non-standard date range operations and conditional aggregations. While initial attempts with LINQ produced some results, the generated SQL was incredibly inefficient, often resulting in multiple round trips and huge temporary tables on the database server. After careful profiling, the team scrapped the LINQ approach for this specific page and replaced it with a single, highly optimized SQL stored procedure. Invoking this procedure through from SQL Raw transformed the dashboard's load time from 30+ seconds to under 2 seconds, proving that sometimes the most advanced solution is a well-crafted piece of plain SQL. 8.3 The lazy loading lure. When convenience turns into curse. Lazy loading, while seemingly convenient, is a feature that often backfires catastrophically in performance-sensitive applications due to its propensity to reintroduce the N+1 problem. What it is? Lazy loading means that related entities or collections, e.g., an order's order items, are not loaded from the database immediately when the principal entity, order, is retrieved. Instead, they are loaded only when they are first accessed in your C hash code. This typically requires navigation properties to be virtual and the Microsoft .entity framework core.proxies package to be installed, which generates runtime proxies that intercept property access. Why it's a problem? Reintroduction of N+1. This is the biggest issue. If you load a list of orders, e.g., 100 orders, and then iterate through them, accessing order items for each, EF core will execute a separate query to fetch the order items for each order. This is the classical N+1 problem. It's often insidious because the queries are triggered implicitly by property access in your C hash code, not explicit LINQ queries. Unexpected database round trips. Developers often don't realize that accessing a property is triggering a database query. This can lead to many small, inefficient queries happening unexpectedly throughout the code. Difficulty in debugging. Because the queries are implicitly triggered, it can be hard to pinpoint the source of performance issues. Profiling becomes essential. Increased network latency. Each implicit query involves a separate network round trip to the database, compounding latency. Example scenario: you have list products equals context.products.list. Your product entity has a virtual list review reviews, get, set property enabled for lazy loading. Later in your display logic, you iterate for each var product in products, write line product.name, for each var review in product reviews, write line review.comment. This simple loop will cause a separate database query for the reviews of each product, leading to an N+1 problem. How to identify database profiler. The most effective way is to use a database profiler. You'll see a storm of select statements for related entities after an initial query, often repeating patterns of select, where id equals X unusual number of database calls. If your application is making many more database calls than you expect for a screen or operation, lazy loading is a prime suspect. No explicit includes when related data is needed. You need related data, but your query doesn't use include. This is a classic lazy loading scenario. How to fix? Eager loading with include preferred. This is almost always the best strategy. Explicitly load related data when you know you'll need it within the same unit of work. Context.products.include p equals peer reviews to list. This resolves the N+1 problem by using a single join or a few as-split query calls. Projection with select. If you only need a subset of data from related entities, use select to project into a DTO. This avoids loading entire entities and their graphs. Disable lazy loading. For most new applications, it's often best to disable lazy loading by default, either by not installing the Microsoft .entity framework core.proxies package or by explicitly configuring it. This forces you to think about data loading explicitly. If you truly need it for specific cases, you can enable it per query using explicit load calls on navigation properties. Preventative measures. Explicit data loading policy. Establish a clear policy for data loading. Eager load with include or project with select everything you need. Avoid relying on implicit loading. Code reviewers. Train code reviewers to look for virtual navigation properties or scenarios where related data is accessed without explicit includes. Integrate profiling in development. Make database profiling a regular part of your development and testing process. Anecdote. A newly launched project management application began experiencing severe slowdowns in its project overview screen as soon as it accumulated more than a few dozen projects. The screen loaded a list of projects, and for each project, displayed its associated tasks, team members, and recent activity feed. The initial query was a simple context.projects.list. All related collections, tasks, team members, activity feed were marked virtual for lazy loading. The system was generating hundreds, sometimes thousands, of individual queries to fetch these related collections, one by one for each project displayed on the screen. The fix involved adding explicit include statements to the initial project's query. Context.projects.include p equals p tasks. Include p equals p team members. Include p equals p activity feed to list. The performance immediately shot up, turning a slow, unusable screen into a snappy, responsive one. 8.4 Compiled queries, when micro-optimizations matter. Compiled queries are an advanced optimization technique for very specific, performance-critical scenarios, where the same LINQ query is executed repeatedly with different parameters. What it is, when EF Core executes a LINQ query, it first has to translate that LINQ expression tree into SQL. This translation process has a small overhead. For queries that are executed thousands or millions of times per second, e.g., in a high-throughput API, this overhead, though small per query, can add up. Compiled queries precompile the LINQ expression to SQL once, caching the translation, so subsequent executions using different parameters skip the translation step. Why it's a problem? Limited impact. For most applications, the performance gain from compiled queries is negligible. The overhead of LINQ to SQL translation is usually very small compared to network latency, database query execution time, or application logic. Complexity. Compiled queries add complexity to your code. They require defining static delegate functions and managing their parameters carefully. Reduced readability. The code for compiled queries is less straightforward than standard LINQ queries. Potential for abuse. Developers sometimes apply compiled queries universally, believing them to be a magic bullet, without understanding the actual performance bottleneck. This adds unnecessary complexity without real benefit. Example scenario. A high-volume microservice frequently retrieves a user by ID. This query, context.usersWhere, u equals uid equals some ID, first or default, needs to be as fast as possible because it's called millions of times a day. How to identify? Micro-benchmarking. You need to use micro-benchmarking tools, like benchmark.net, to measure the execution time of highly repetitive, parameter-only varying LINQ queries. If the translation overhead consistently shows up as a significant percentage of the total operation time, compiled queries might be beneficial. Profiling query translation. Advanced profilers might show time spent specifically in EF Core's query translation pipeline. How to fix? Define in a static method. Compiled queries are typically defined as static fields. Example for user by id query. Private static read-only func mydb context, int, user getUser by id compiled equals, ef.compile query. Mydb context, int userid, equals context.users first or default, u equals uid equals userid. Usage, user equals getUser by id compiled, context, 123. Preventative measures. Profile first. Only consider compiled queries after profiling has clearly identified LINQ expression compilation as a significant bottleneck. This should be a very late-stage optimization. Focus on major bottlenecks. Prioritize optimizing database I/O, network trips, and high-cost SQL operations, e.g., as discussed in 8.1 and 8.2 before looking at the micro-optimizations of query compilation. Keep it simple. For most queries, standard LINQ is perfectly sufficient and much more readable. Anecdote. A gaming platform's leaderboard service was under extreme load, handling thousands of requests per second. Developers, having optimized the database queries and network stack, started looking for micro-optimizations. They noticed that a specific query to fetch a player's score by ID was called millions of times hourly. They implemented a compiled query for this specific operation. While the individual performance gain per query was indeed tiny, a few microseconds, over millions of calls, it translated into a noticeable reduction in CPU usage on the application servers. This was a rare case where the scale of execution justified the added complexity of a compiled query, emphasizing that such optimizations are typically reserved for the absolute highest throughput, most critical paths after all other major bottlenecks have been eliminated. Chapter 9. The testing tangle, making your EF core code testable. Writing reliable software requires thorough testing. When it comes to data access code, especially with an ORM like Entity Framework Core, testing presents unique challenges. The tight coupling between your application and the database can make unit testing slow, brittle, and dependent on external infrastructure. On the other hand, skipping tests or relying solely on full integration tests can miss subtle bugs and lead to painful regressions. This chapter unravels the testing tangle faced by developers working with EF Core. We'll explore strategies for effectively unit testing and integration testing your data access layer, covering the pros and cons of in-memory databases, SQLite, and mocking techniques for your DB context, all aimed at ensuring your EF Core code is both robust and reliably tested. 9.1 The challenges of testing data access code. Testing code that interacts with a database introduces complexities that aren't present in testing pure business logic. These challenges can deter developers from writing comprehensive tests, leading to fragile applications. What it is? Testing EF Core code involves verifying that your LINQ queries translate correctly to SQL, that data is saved and retrieved as expected, that relationships are handled properly, and that error conditions are managed gracefully. The challenges arise primarily from the fact that EF Core is an abstraction over a database, and databases themselves are external, stateful, and often slow resources. Why it's a problem? External dependency. A real database is an external dependency. It might not always be available, it might be slow, or its state might be unpredictable due to previous test runs or concurrent tests. Speed. Running tests against a real database, even a local one, is significantly slower than running in-memory unit tests. A large test suite can become excruciatingly slow, discouraging frequent execution. State management. Databases are stateful. Each test might modify data, leaving the database in an inconsistent state for subsequent tests. Cleaning up data before or after each test is crucial, but adds complexity. Complexity of setup. Setting up a fresh, known database state for each test or test run requires time and effort. Network latency. Even for local databases, there's some network overhead involved, further slowing down tests. Test isolation. Ensuring that tests are truly isolated and don't interfere with each other's data is a significant challenge when sharing a database instance. Example scenario: you have a product repository that uses my DB context to fetch products. A unit test that instantiates product repository directly would need a configured and available database to run, violating the principle of unit test isolation and speed. How to identify slow test suites. Test suites that take minutes or tens of minutes to run, discouraging developers from running them frequently. Flaky tests. Tests that sometimes pass and sometimes fail without any code changes, often due to shared database state or timing issues. Lack of test coverage. Developers avoiding testing the data access layer because it's too hard or too slow. How to fix? The solution isn't a single silver bullet, but a combination of strategies. You need a testing pyramid that includes unit tests for business logic, mocking the DB context or repository layer when testing pure business logic that consumes data access. Integration tests for data access, running tests against a lightweight, in-memory, or embedded database, like SQLite, for isolated, fast, and reliable testing of EF Core queries and persistence. End-to-end tests, fewer. Running a small set of critical tests against a full, production-like database environment. 9.2 In-memory databases. Convenient, but beware of false positives. EF Core provides an in-memory database provider, which can be incredibly useful for quick, isolated tests. However, it's crucial to understand its limitations. What it is: the EF Core in-memory database operates entirely in your application's RAM. It simulates a relational database. It allows you to define entities, relationships, and perform LINQ queries. Since no actual database interaction occurs, it's extremely fast and easy to set up. Why it's a problem? SQL translation discrepancies. This is the primary pitfall. The in-memory database does not translate LINQ queries to SQL. It uses LINQ to object semantics. This means queries that succeed in memory might fail when run against a real database, e.g., due to an untranslatable method or a subtle difference in string comparison. Conversely, features that are database-specific, like database functions, computed columns, or case sensitivity in string lookups, will not be correctly simulated. No transactions or isolation levels. The in-memory database doesn't support complex database features like transactions, isolation levels, optimistic concurrency tokens, row version, or stored procedures. Tests relying on these features will provide false positives. No real schema enforcement. It doesn't enforce database-level constraints like unique key constraints, check constraints, or complex foreign key on delete rules as rigorously as a real relational database. Concurrency issues not caught. It cannot simulate how a real database handles concurrent access. Example scenario. You write a linq query that uses string dot contains with string comparison ordinal ignore case. This might work in the in-memory database because C-hash strings can do comparison, but the underlying SQL database might be case-sensitive depending on collation, causing different behavior in a real environment. Or you forget to set up a unique index on user email. The in-memory database won't complain if you add a duplicate, but a real database would throw an exception. How to identify? Tests pass in CI, fail in production. This is the classic symptom. Your test suite passes flawlessly, but when deployed to a real environment, the same functionality fails. Lack of database-specific error simulation. You attempt to test error handling for unique key violations or foreign key constraints, but your in-memory tests never trigger these errors. How to fix? Use for unit testing of repository services. In-memory databases are excellent for testing the logic within your repositories or services, ensuring that entities are added, updated, and queried correctly as C-hash objects from EF Core's perspective. They verify that your data access methods assemble the correct linq expressions. Supplement with integration tests. Never rely solely on in-memory tests for your data access layer. They must always be supplemented with a layer of integration tests that run against a real, even if lightweight, relational database. Isolate test cases. For each in-memory test, ensure you create a fresh DB context instance with a unique database name. This guarantees test isolation. Public class product service tests. Private MyDB context get DB context, string database name. var options equals new DB context options, builder MyDB context. Use in-memory database name. Database name, unique name per test. Options var context equals new MyDB context, options. Optional, seed data for this specific test. Context.productSaid, new product. A context save changes, return context. Fact, public void add product saves product directly. Using var context equals get DB context. Add product saves product correctly. Var service equals new product service, context. Service add product, new widget. Assert single context.productswhere, p equals p.name equals new widget. Preventative measures, understand limitations. Educate your team about the in-memory database provider's limitations, especially regarding differences in linq to SQL translation and database feature support. Focus on logic, not implemented features. Use in-memory for testing the logic of your linq queries and data manipulation, not for verifying database-specific behaviors or optimizations. Anecdote case study. A development team used the EF Core in-memory database exclusively for testing their new user registration module. Their tests passed perfectly, which included a check for unique email addresses. However, when deployed, users consistently reported duplicate key errors despite entering seemingly unique emails. The root cause was that SQL Server's varchar columns, the default mapping for C-hash string, were configured with a case-insensitive collation, while their C-hash in-memory-based tests were fundamentally case-sensitive. The in-memory database allowed test at example.com and test at example.com as distinct entries, while their production SQL Server database considered them duplicates, leading to validation errors. This highlights the dangers of relying solely on the in-memory provider for testing database-specific behaviors. 9.3 SQLite for integration testing, a closer-to-real alternative. For robust integration testing of your EF core code, a lightweight, file-based relational database like SQLite is often a superior choice to the in-memory provider. What it is. SQLite is a self-contained, serverless, zero-configuration, transactional SQL database engine. EF Core has a provider for SQLite. For testing, you typically configure EF Core to use an in-memory SQLite database, data source equals memory, or a temporary file-based one. Why it's better than in-memory. Real SQL translation. SQLite performs actual SQL translation and execution. This means queries that fail to translate or translate inefficiently will be caught. Enforces schema. SQLite enforces many common relational database constraints, including unique keys, not null, foreign key constraints, and default values. This catches more bugs related to schema definition. Supports transactions. SQLite supports full ACID transactions, allowing you to test complex transactional logic more accurately. Faster than full database. While still slower than the in-memory provider, it's significantly faster than spinning up a full SQL server or PostgreSQL instance for every test. Why it's not perfect. SQLite-specific features. While better than in-memory, SQLite implements a subset of SQL. Advanced database-specific features, e.g., SQL Server's row version for optimistic concurrency, specific functions like DATEADD, complex locking behaviors, stored procedures, will still not be fully supported or accurately simulated. Slightly slower. It will still be slower than the in-memory provider due to actual query parsing and execution. Example scenario: you want to test your user repository, which uses user email as a unique index. Using SQLite, you can attempt to add 2 users with the same email and expect a DB update exception, just like a real database. How to fix. Configure for in-memory SQLite. Use SQLite, data source equals memory. In your DB context options builder for rapid in-memory testing. Crucially, open and keep the connection alive throughout the test run, otherwise the in-memory database will be lost. Public class user repository tests. iDisposable. Private DB context options, my DB context options. Private SQLite connection. Keep connection open. Public user repository tests. Connection equals new SQLite connection. Data source equals memory. Connection open. Open connection to keep in-memory DB alive. Context options equals new DB context options. Builder my DB context. Use SQLite connection. Options. Ensure schema is created once per test fixture. Using var context equals new my DB context. Context options. Context database ensure created. Optional. Seed initial data for tests. Test methods will use new my DB context. Context options. Fact. Public async task. Add user with duplicate email throws exception. Using var context equals new my DB context. Context options. Context.usersadd. New user. Email equals test@example.com. Await context save changes async. Using var context equals new my DB context. Context options. Context.usersadd. New user. Email equals test@example.com. Await assert throws async DB update exception. Equals context save changes async. Public void dispose. Connection close. Test fixtures for setup teardown. Use iClass fixture or collection definition in XUnit to set up a shared context options and connection for a suite of tests, ensuring schema creation only happens once. Seed test data. Seed specific data for individual test cases or scenarios within transaction boundaries to ensure isolation and a known state for each test. Preventative measures. Mix and match. Use SQLite for most of your integration tests, but still reserve some end-to-end tests for your actual production database system if you rely heavily on its specific features. Clear boundaries. Define which tests use in-memory, which use SQLite, and which use a full database. Anecdote. After the case insensitivity incident, the team decided to migrate their EF core tests from the in-memory provider to SQLite. They were able to catch more subtle bugs related to database constraints and date-time handling, because SQLite accurately reflects how SQL handles these operations. For instance, they discovered an issue where their date-time property, which was intended to store dates without time zones, was being incorrectly compared in some LINQ queries due to EF Core's default date-time offset handling when mapped to a database. SQLite's more faithful SQL translation helped identify this problem before it reached production, proving its value as a compromise between speed and fidelity. 9.4 Mocking DB context for unit testing business logic. While you want to test your EF core queries, you don't want your pure business logic unit tests to have a dependency on any database, even an in-memory one. This is where mocking comes in. What it is? Mocking involves creating lightweight, simulated versions of external dependencies, like your DB context or DB sets, to control their behavior during unit tests. This isolates the code under test, making tests faster, more predictable, and truly independent. Why it's a problem? Tight coupling. If your business logic directly instantiates DB context or DB sets, it becomes difficult to unit test without an actual database. Violates unit test principles. True unit tests should be isolated, fast, and repeatable with no external dependencies. Testing side effects. If you're testing business logic that interacts with a repository, you want to test the logic, not the repository's database interaction itself. That's for integration tests. Example scenario. You have an order processing service that takes a MyDB context or an iOrder repository as a dependency. When testing the order processing service's logic, e.g., calculating discounts, validating inventory, you don't care about actual database calls. You just need the DB context or repository to behave predictably. How to fix? Interfaces for repository services. Always design your data access components, repositories, or the DB context itself if passing it directly using interfaces. This allows you to easily substitute real implementations with mock implementations during testing. Example: public class order processing service, private read-only iOrder repository order repository, public order processing service, order repository order repository equals order repository. Then, in your test, you can mock iOrder repository. Mocking frameworks. Use a mocking framework like mock or nsubstitute. Mock DB set and DB context. You can create mocks of DB context and DB set quite effectively, especially if you ensure your LINQ queries for data access methods return a queryable T. Using mock, using system link, using system.collections generic, public class order processing service tests. Fact, public void calculate total applies correct discount. 1. Create a mock DB set. var mock products equals new list product. New product id equals 1, price equals 100. New product id equals 2, price equals 50. As queryable, var mock set equals new mock DB set product. Configure mock set to return data when queried. Mock set as a queryable product, setup m equals m.provider. Returns mock products.provider. Mock set as a queryable product, setup m equals m expression. Returns mock products expression. Mock set as a queryable product, setup m equals m element type. Returns mock products element type. Mock set as a queryable product, setup m equals m get enumerator. Returns mock products get enumerator. 2. Create a mock DB context. var mock context equals new mock MyDB context. Configure mock context to return the mock DB set when products is accessed. Mock context setup c equals c.products returns mock set object. 3. Instantiate the service with the mock context. var service equals new order processing service mock context object. 4. Act and assert. var total equals service.calculate order total new listant 1 2. Assert equal 135.0 total, assuming 10% discount logic. Preventative measures. Dependency inversion principle. Design your classes so they depend on abstractions interfaces rather than concrete implementations. This enables easy mocking. Clear separation of concerns. Keep your pure business logic separate from your data access concerns. Your order processing service should depend on iOrder repository, not directly on DB context. Test what matters. Remember that for unit tests, you're testing the logic within the service, assuming its dependencies, like the repository, behave as expected. You're not testing if the mock actually persists data to a database. Anecdote: a complex legacy system was being refactored, and its central order calculation engine class was tightly coupled to a static data access layer that directly instantiated DB context. Any unit test for the engine required a fully running database, making the test sweet, slow, and difficult to maintain. The team adopted dependency injection and introduced an iProduct repository interface. The order calculation engine was refactored to depend on iProduct repository. This allowed them to mock iProduct repository in their unit tests, providing controlled product data and mocking the getProductById method. This simple architectural change allowed them to write fast, isolated unit tests for the core calculation logic, significantly improving development velocity and test reliability. Chapter 10: Beyond the Blunder. Best Practices and Continuous Improvement. We've journeyed through a landscape fraught with entity framework core pitfalls and explored common mistakes that can plague applications. From the insidious N+1 problem to the complexities of DB context lifecycle, the dangers of manual migration edits, and the intricacies of testing, we've dissected many ways EF Core can lead you astray if its nuances aren't understood. This final chapter serves as a synthesis, reinforcing overarching best practices that transcend individual pitfalls. It's a call to proactive development, continuous learning, and robust monitoring, ensuring that your EF Core journey is marked by performance, stability, and maintainability, rather than perpetual blunders. 10.1 Reinforcing Core Principles. The EF Core Developer's Mantra. Many of the specific solutions discussed throughout this book boil down to a handful of fundamental principles. Adopting these as a developer's mantra for EF Core will naturally steer you away from most common pitfalls. Transparency and intentionality. Don't treat EF Core as a black box. Understand what SQL it's generating, how it's tracking changes, and what its methods are truly doing. Be intentional about your data access strategy rather than relying solely on conventions and hoping for the best. Action. Regularly use SQL profiling tools, e.g., mini-profiler DB context logging, to inspect the generated SQL. Question seemingly innocent LINQ queries. Explicit data loading. Avoid implicit loading mechanisms wherever possible. This means being wary of lazy loading, unless you have a very specific, managed use case, and always thinking about what data you truly need for a given operation. Action. Always use include for eager loading, or select for projecting data into DTOs, to load precisely what's required in as few database trips as possible. Keep DB context lifespan short and scoped. DB context instances are designed to be light, ephemeral, and single-threaded. Conflating their lifecycle with longer-running application concerns is a direct path to memory leaks, stale data, and concurrency issues. Action. Configure DB context with a scoped lifetime in your dependency injection container. Recreate and dispose DB context instances for each unit of work, e.g., per web request, per message, per background job execution. Strict adherence to testability principles. Design your code for testability from the outset. This means favoring dependency injection, interfaces for data access layers, and understanding the nuances of different testing approaches, in-memory versus SQLite versus full database. Action. Implement a strong testing strategy that includes unit tests, mocking data access, and integration tests using SQLite or a lightweight test database. Data integrity first. Prioritize the correctness and consistency of your data above all else. Prevent lost updates, ensure proper transaction boundaries, and handle exceptions gracefully. Action. Implement optimistic concurrency for modifiable entities. Wrap critical operations in explicit transactions where atomicity is required, and create robust error handling for save changes. Failures. 10.2 The importance of monitoring. Catching blunders in production. Even with the best development practices, unexpected performance issues or data problems can emerge in production environments. especially as data volumes grow and user load increases. Proactive monitoring is your early warning system. Application Performance Monitoring, APM, integrate APM tools, e.g., Application Insights, New Relic, Dynatrace into your applications. These tools can collect metrics on database query execution times, CPU memory usage, and overall request latency, helping you identify slow endpoints or database operations. Database-specific monitoring. Leverage the monitoring and profiling tools provided by your database system, e.g., SQL Server Management Studio Activity Monitor, PostgreSQL PG Stat Statements, MySQL Workbench. These tools can show you long-running queries, queries not using indexes, deadlocks, and overall database resource consumption. EF Core Logging. Configure EF Core to log generated SQL queries. In a development environment, this can be verbose logging to console or debugger. In production, consider logging warning and error events to structured logging systems, e.g., Serilog, Nlog, Log4net, that route to centralized logging platforms, e.g., Elasticstack, Splunk. This helps you inspect problematic queries in a production context without full, noisy profiling. Custom health checks. Implement custom health checks that perform a simple database query to verify connectivity and basic data access. Make these part of your application's health endpoint and monitor them. Action. Set up alerts for deviations from baseline performance metrics, e.g., average query time exceeding a certain threshold, sudden increase in DB update concurrency exception count. Regularly review database and application logs for unusual patterns. 10.3 Staying updated. The evolving landscape of EF Core. Entity Framework Core is a continuously evolving product. New features are added, performance is improved, and bugs are fixed with each release. What was a pitfall in one version might be mitigated in a later one, or new best practices might emerge. Follow official documentation. The official Microsoft documentation for EF Core is an excellent, continuously updated resource. It covers everything from basic usage to advanced tuning and known issues. Monitor release notes. Keep an eye on the release notes for new EF Core versions. They highlight new features, breaking changes, and performance improvements that could impact your applications. Engage with the community. Participate in community forums, follow reputable blogs, and attend relevant conferences or webinars. The EF Core community, Stack Overflow, GitHub discussions, is active and a great source of practical advice and solutions. Gradual updates. Plan for gradual updates to newer EF Core versions. Test thoroughly in development and staging environments before deploying to production. Be aware of any breaking changes. Performance benchmarks. Be aware of common performance benchmarks and how different EF Core versions or configuration choices impact them. Action. Subscribe to the Net blog, follow EF Core team members on social media, and set aside dedicated time for exploring new features and improvements in each major EF Core release. Factor in upgrades as part of your regular maintenance cycle. 10.4 The power of simplicity and focused responsibility. Finally, amidst the complexity of ORMs and databases, remember the power of simplicity and clear responsibility. Simple models. Keep your entity models as simple as your business domain allows. Avoid overly complex inheritance hierarchies or overly generic models that make mapping and querying difficult. Clear separation of concerns. Maintain a clear boundary between your business logic and your data access logic. Services should focus on business rules, delegating persistence details to repositories or dedicated data access classes. Don't over-engineer. Avoid premature optimization or implementing complex patterns unless there's a clear, measured need. Start simple, profile, and optimize only where bottlenecks are identified. Aggregate routes and bounded contexts. In larger applications, consider architectural patterns like domain-driven design, which advocates for aggregate routes and bounded contexts. Designing your data models around consistent transactional boundaries can drastically simplify data manipulation and improve data integrity discussions, reducing EF Core usage to the specific interaction with each aggregate. Action. Regularly refactor your codebase to simplify complex data access patterns. Prioritize readability and maintainability. Only introduce advanced optimization techniques or complex patterns when truly justified by measurable performance gains. Conclusion: Entity Framework Core is an incredibly powerful and productive ORM that can dramatically accelerate your development process. However, its abstraction can sometimes obscure the underlying database realities, leading to a range of pitfalls, from performance degradation to data integrity issues. By understanding these common blunders, adopting proactive best practices, and committing to continuous learning and monitoring, you can harness the full potential of EF Core, building robust, high-performance, and maintainable data-driven applications. The journey of software development is one of continuous learning and adaptation. May your EF Core applications thrive, free from the entanglements of common pitfalls.